Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us deep into the very fabric of reality, into the story of atoms. Not just the chemistry class kind, but the ones that shape the stars, the ones floating now through your bloodstream, the ones that might one day rest in a comet's icy tail or in the warmth of a baby's breath. These tiny invisible anchors hold everything together: life, death, and the slow drift of galaxies through time. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the atoms that make up everything. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Take a deep breath, soft and slow. Let your shoulders fall. Let your jaw release, your hands rest, and your thoughts begin to float like dust motes caught in sunlight. Let's go back, not just decades or centuries, but all the way back. Back to before memory, before stars, before time as we know it. Imagine a universe so young it hasn't even taken its first breath. There are no galaxies yet, no planets, no atoms, not even light as we recognize it. Just energy, pure, boundless, boiling energy, everywhere and nowhere at once. And from this seething field of possibility, the smallest pieces of existence began to flicker into being. We're going to follow them, gently, carefully, from their chaotic birth in the aftermath of the Big Bang, to their calm companionship in your breath, your bones, your beating heart. We'll look at how atoms came into existence, how they hold themselves together against the push and pull of cosmic forces, and how they continue to shape every corner of the universe, from collapsing stars to a steaming cup of tea. Atoms are storytellers, quiet ones. They don't shout, they don't rush, but they remember everything. They've been part of exploding suns and frozen lakes, of ancient forests and future cities. Some of the atoms in your body were once in the smoke of a fire 1 million years ago. Others might have lived inside a dinosaur, or floated through the lungs of someone long forgotten. They never stop moving, they just change companions. Tonight, we'll wander through their timeline. We'll visit the moments when they first formed, when the universe cooled just enough for electrons to settle into place. We'll sit with the stars, watching as atoms fuse, combine, and burst apart again in stellar death. We'll peer into cells, where atoms whisper messages and form the building blocks of life, and we'll contemplate the end. What happens to atoms when everything fades and heat gives way to silence? But don't worry, we won't rush. This isn't a science sprint, it's a slow float through atomic stillness, like mist curling over a quiet pond, like the hush of snowfall on a city street at night. So wherever you are, wrapped in blankets, curled on a couch, or lying still beneath a ceiling that's seen 1,000 thoughts, know that right now, the atoms around you are calm, they're steady, they've seen universes come and go, and tonight, they're holding space for you. Let's begin. If you were to hold out your hand right now, just quietly raise it into the dim air, you wouldn't see them. But trillions of atoms are there, nestled in your skin, gliding through your blood, tracing the ridges of your fingerprint. They're in the warmth of your palm, the breath between your lips, the air that drifts across the room. Invisible and quiet, yes, but not absent. Atoms don't call attention to themselves. They're not flashy, not dramatic. But without them, nothing you know could exist. No trees, no stars, no music, no memory. And strangely enough, they almost didn't exist at all. You see, the early universe didn't exactly roll out a welcome mat for atoms. The first few minutes after the Big Bang were intense, wild, temperatures that could boil atomic nuclei apart. Photons, the particles of light, were too energetic, so energetic that they knocked electrons off of anything that dared to try forming. Atoms were trying to come together, trying to hold hands, and photons just kept slapping them apart. For thousands of years, matter and light were locked in this kind of cosmic chaos. It's hard to imagine, isn't it? A universe where light doesn't travel freely, where space is thick like fog with no direction, where structure can't yet emerge because nothing is allowed to stay still. And yet, slowly, gently, the chaos cooled. The universe began to stretch. Like warm dough rising, the pressure eased. Energy spread out. Photons lost their fire. And then, in a moment of staggering calm, electrons found their way home. This moment, called recombination, happened about 380,000 years after the Big Bang. The temperature had dropped enough for protons and electrons to link up and form the first real atoms, mostly hydrogen, with a sprinkling of helium. Suddenly, the fog lifted. Light could move. The cosmos, for the first time, became visible. Imagine that. A universe full of atoms for the very first time. A silent, glowing expanse of neutral hydrogen. No stars yet. No galaxies. Just simplicity. Stillness. The building blocks of everything waiting. And in that stillness, atoms began to gather. They pooled into denser patches. Gravity, patient, tireless gravity, gently pulled them together. Over millions of years, these clumps would collapse into stars. Those stars would burn, fuse atoms into heavier elements, and when they died, violently, they would scatter those atoms back into the void. And from that stardust, planets would form. Oceans would gather. Molecules would twist into spirals. Life would open its curious eyes. But we're getting ahead of ourselves. For now, just picture the atoms in your body, the carbon in your bones, the calcium in your teeth, the iron in your blood. All of them born in places you'll never see, in stellar hearts and supernova skies, pieces of ancient suns, handed down through time, recycled across galaxies, borrowed just for a little while to make you. You, sitting here now in the quiet, listening, breathing. You're a story those atoms chose to tell, and tonight we're going to follow their journey, from fiery beginnings to peaceful endings, from particle to presence, from silence to structure. But don't worry about remembering every detail. This is a story meant to drift through you, to ease you into sleep if that's where you're headed, or just to sit beside you, like a quiet friend as the world slows down. So let's follow the atoms now. Let's go all the way back to their true beginning, to a time when the universe had no structure, no stars, no shape, just potential, and one great glowing breath about to become something more. Close your eyes if you haven't already, and now picture this, a time so early, so raw, that time itself had only just begun, a moment so small it can't be called a second, not yet. The clock hasn't quite learned to tick. There's no space, no stars, no planets, no atoms, no you, no me, just something. Or perhaps more accurately, everything. But in its wildest, least defined form, the universe, in its first breath after the Big Bang, is not quiet, it's not calm, it's not dark, it is searing, radiant, and restless. So dense and so hot that anything resembling structure simply cannot survive. You can imagine it, though faintly, as a storm without sky, a fire without flame, an ocean of energy without edges. Here, temperatures are measured in trillions of degrees, Particles flare into being and vanish again before they can introduce themselves. There's no room for stability, no stillness. This isn't yet a world where atoms can rest beside each other. This is a universe made of pure energy, boiling, bouncing, blinding, and yet, in the heart of that chaos, something astonishing is happening. This soup of energy is not empty. It's filled with light and potential. Particles are trying to form, quarks, gluons, photons, all racing, all interacting in this primal ballet. But everything's too hot, too fast, too unstable. The universe is a child having a tantrum, all potential and no patience. Atoms, the quiet companions of life and matter, don't exist here. They can't. They require temperature, space, calm. And in this moment, none of those things are available. The energy is so high that if an electron even tried to sit near a proton, it would be immediately blasted away by a stray photon, as if the universe was saying, not yet. Even the most basic pieces of matter, quarks, aren't yet willing to stay bound together. They exist, but only loosely. They drift in a hot plasma with their sticky glue, gluons, barely able to pull them close before the storm tosses them apart again. This is the quark-gluon plasma, a name that sounds clinical but describes one of the wildest states reality has ever known. It's not matter, it's not energy, it's a mess of both. And it filled the early universe for only the briefest of moments, but from it, everything we now know would be born. And perhaps the most surprising part, this madness cooled. The universe began to expand, not slowly but swiftly, like a balloon inhaling infinite air. And with that expansion came relief. Energy stretched out. The wild heat began to fade. Just enough. Enough for the quarks to come closer, to link arms, to begin the work of becoming something more. Atoms at this point were still a long way off, but the idea of them, tiny invisible anchors of structure, was no longer impossible, just improbable, just waiting. So here we pause, in a universe not yet friendly to form, in a moment where light itself is too wild to be seen, where nothing can hold, but everything is on the verge of becoming. From here, we begin to drift forward, just a little, just enough for particles to begin finding each other in the chaos. Because all the quiet beauty of atoms, their loyalty, their bonds, their stories, starts here, in a place of noise and fire, where they hadn't yet found the calm to exist, but they would, and soon. So, the universe has cooled, just a little. Still far too hot for atoms, but no longer so violent that everything flies apart the moment it forms. The tantrum is softening, the expansion continues, and in this fragile, flickering calm, the first true structures begin to emerge. These are not yet atoms, not even close, but something new is stirring in the firelight. You might imagine them as small clusters of determination, quarks, the tiniest building blocks of matter, deciding it's time to stay close. Quarks don't like to be alone. They prefer company, though not just any arrangement will do. They form in threes, and only in specific combinations, like dancers following invisible steps in a pattern written by the laws of physics. With the help of gluons, their tireless companions, they snap together into new forms. These are protons and neutrons, the foundational particles that will one day rest at the centre of every atom in the universe. But right now, they're just newcomers, just whispers of solidity in a world still made of light and flame. The gluons are the secret here. They're the messengers of the strong nuclear force, one of nature's great binding agents. Unlike gravity, which pulls gently across space, or the electromagnetic force, which sparks lightning and magnets, the strong force works at the tiniest scales. It pulls quarks together with such strength that once they're bonded, they can't be torn apart without tearing reality a little too. It's not flashy, the strong force. It doesn't create galaxies or bend starlight, but it does something just as profound. It holds things together when nothing else can. This is how protons are born. 2 up quarks and 1 down quark, dancing in a perfect trio. Neutrons follow close behind, 2 downs, 1 up. It's a subtle change in recipe, but one that makes all the difference. In this early moment, protons slightly outnumber neutrons, and that balance will shape the entire future of chemistry. Now, you might think of a proton as a tiny marble, solid, still, self-contained. But it's nothing like that. It's a storm in miniature, a swirling cloud of energy and movement. It's 3 quarks zipping and bouncing inside, bound so tightly they can never escape. The proton is stable, reliable, long-lived. Most of the protons formed in this moment still exist today, quietly spinning inside your body. That's worth repeating. The protons in your fingertips, in your bones, in the air you breathe, maybe over 13 billion years old. They've never aged, never changed, just drifted from place to place, partner to partner, waiting for the right combinations. It's one of the universe's quieter miracles that something so small, so invisible, can last for so long. That these ancient particles could survive supernovae, galaxies forming and collapsing, planets boiling and freezing, only to end up in a cell in your body listening to this story. And while protons and neutrons are settling into existence, the rest of the universe is still a blur. Electrons, light, fast, elusive, flit about, not yet willing to stay near anything for long. Photons still zip through everything, preventing any kind of calm bonding. But in this moment we have the first hints of something new. Nuclei, tiny hearts of future atoms, waiting for a future they can't yet see. The universe is still young, still wild. But it has learned one small lesson: how to hold something together. And that, as it turns out, changes everything. Now that we have protons and neutrons, little knots of matter held tightly by the strong force, the universe is ready to try something bold, combining them. Not just holding particles in threes, but stitching them into something larger. Something that hints, for the first time, at the atoms we know today. But time is short. This phase of cosmic history lasts just a few minutes. Not millions of years, not even hours, just minutes. Between about 3 and 20 to be specific. The conditions are fleeting. The universe is still incredibly hot but cooling fast. Falling below 1 billion degrees Kelvin, which is still far hotter than any star today, but just cool enough for magic to begin. This is the era of Big Bang nucleosynthesis, a grand term for a surprisingly simple recipe. In this brief moment, protons and neutrons begin to fuse. They form deuterium, 1 proton and 1 neutron bound together. That deuterium quickly grabs another proton to become helium-3, or another neutron to become tritium. Some combinations stick, others fall apart. But slowly, steadily, the early universe begins producing helium, real atomic nuclei, made of 2 protons and 2 neutrons. It's like a cosmic assembly line, and for a few minutes it's surprisingly efficient. Hydrogen, of course, is everywhere. Just a single proton, or a proton plus an electron when it becomes a full atom. But here, in this brief window, helium becomes the second born. About 25% of the universe's matter, by mass, ends up as helium nuclei, forged in these few minutes. There's even a trace amount of lithium, a shy third element, made in such small quantities that it barely leaves a signature. And then, it stops. The universe cools too much. The energy needed to fuse heavier elements like carbon or oxygen is no longer available. The factory shuts down. Nuclear synthesis ends. You might wonder, why couldn't it go further? Why didn't the universe just make all the elements right then and there? The answer is partly time, partly balance. Heavier elements require more complex reactions, more time to gather the right components. And in this early universe, everything is expanding. Quickly, matter thins out. The clock runs out before those more intricate atoms can be born. So we're left with a universe that is astonishingly simple, elementally speaking. Mostly hydrogen, a good amount of helium, a whisper of lithium. That's it. And yet, that was enough. These light elements will go on to fuel stars, shape galaxies, form water, build life. Almost everything you've ever touched, eaten, breathed, or loved began with the products of this brief nucleosynthesis moment. It's humbling, really, to think that the entire elemental foundation for the universe was laid down in under 20 minutes, in a time before stars, before planets, before memory. And those hydrogen atoms, many of them are still with us today. Hydrogen doesn't decay, it doesn't fade. The hydrogen in your water glass, in your breath, in the clouds above you, some of it may be as old as the universe itself. You carry that history without ever noticing, and now you know it's there. A quiet legacy of the universe's very first attempt at making something solid. We'll pause here. In this brief stillness after the forge, the fire has cooled, but the stage is set. The universe holds its breath. The atoms aren't quite here yet, not fully, but the pieces are waiting. The script has been written in helium and hydrogen, and the next chapter is about to unfold. Now we enter a strange and quiet stretch of cosmic time. The fire of creation has passed. The early nuclear forge, so brief, so brilliant, has cooled. Hydrogen and helium nuclei float through space, newly minted, light as whispers, patient as clouds. But something is still missing. We don't yet have atoms. That might sound odd. Weren't hydrogen and helium just formed? Yes, their nuclei were the cause, the centres of future atoms. But a complete atom, as you may recall, needs more than just a centre. It needs an electron, a tiny, nimble companion that dances around the nucleus, creating the structure we recognise as matter. Without electrons in orbit, these nuclei are just bare seeds. And right now, in this early universe, electrons are everywhere. They zip and swerve between particles light as mist, but they cannot settle, they cannot attach, they cannot rest. Why? Because the universe is still too hot. Not hot enough to split nuclei anymore, no, but still warm enough that photons, the particles of light, are far too energetic. They ricochet across space like tiny bullets, constantly smashing into any loose electrons and knocking them free from whatever they try to bond with. Imagine trying to sit down in a chair while someone keeps yanking it out from under you. That's what it's like for an electron in this era. Every time it gets close to a proton, some overexcited photon barges in and says, "Not yet." This strange situation lasts a long time, hundreds of thousands of years. The universe is expanding, yes, and cooling steadily, but the conditions just aren't right for atoms to form. Instead, we have a hot, dense plasma, a glowing soup of free-floating electrons, protons and helium nuclei, all tangled with radiation. This plasma is opaque. You can't see through it. Light itself can't travel very far without being scattered. It's as if the whole universe is wrapped in a glowing fog. There are no stars yet. No galaxies, no structure, just energy, drifting particles, and silence that hasn't learned how to be dark. This time is often called the photon era, or sometimes more poetically, the foggy universe. It's a pause, a waiting room. All the pieces are there, but none of them have taken their places yet. And so, the universe waits. It stretches, it cools, it relaxes, ever so slowly into a state where stability might finally be possible. And in this pause, a kind of quiet anticipation builds. Think of the universe like dough rising under a cloth. You can't see the movement, but something is happening. The pressure is changing. The ingredients are rearranging. The heat that once destroyed is starting to soften. We're approaching a threshold. Soon, very soon, electrons will be able to stay, photons will begin to lose their grip, and when that happens, something magical occurs, but not yet. For now, we stay in this luminous, invisible fog. A place where matter can't quite take shape, where light can't quite escape. A liminal time, a cosmic breath being held. Atoms are coming, just a little longer. And then it happens. After hundreds of thousands of years wandering in luminous fog, the universe finally cools to just the right point, about 3,000 degrees Kelvin. Still hot by earthly standards, yes, but now cool enough for something delicate and profound to unfold. Electrons for the first time are able to rest. They slow, they settle, and they begin to spiral gently toward waiting protons and helium nuclei. Not with force, not with drama, but with quiet inevitability, drawn together by the soft pull of electromagnetism. And this time, the photons don't interfere. The light no longer has the energy to tear them apart. This is the moment known as recombination. It's a gentle word for a monumental event. Across the entire universe, scattered particles are pairing up, electrons binding to nuclei, forming the first complete atoms. Mostly hydrogen, of course, with some helium and the faintest whisper of lithium. These newborn atoms are electrically neutral, and that changes everything. Because now light can travel. Before this, photons were trapped, bouncing endlessly between particles, unable to move freely like echoes with no hallway to pass through. But with the formation of neutral atoms, the fog lifts. Space becomes transparent. Light is finally released, and it travels still. That light, the one that began moving freely at this exact moment, is what we now call the cosmic microwave background, or CMB. It is the universe's first visible memory, a faint uniform glow that still surrounds us today. Not as light we can see with our eyes, but as a gentle microwave signal, everywhere, all the time. The echo of a universe becoming clear. Imagine that, every night when you look up at the stars, or when you close your eyes and think of space. You're drifting beneath the afterglow of this ancient moment, the light from when atoms first came into being, the universe's very first sigh of calm. We often think of creation as loud, explosive, chaotic, but this was quiet. Recombination didn't make noise, it made clarity, it gave light a path, it gave structure a chance. Now that atoms can exist, they can begin to do what atoms do best. Gather, fall together, form clouds, collide, and eventually, under the patient hand of gravity, spark stars into being. But that's still a little way off. Right now, the universe is filled with hydrogen and helium gas. No galaxies yet, no suns, just a vast, darkening sea of neutral atoms floating freely in an expanding cosmos. It's a remarkably peaceful picture, especially compared to the fireworks of earlier epochs. The fog has lifted. The light has stretched its arms. The universe, for the first time, can see itself. And we, much later, would come to see it too. We would build satellites and detectors to catch the faint hiss of that original light. We'd turn it into colourful maps, radiant patterns that show the earliest fingerprints of structure, ripples in the CMB that hint at everything to come, galaxies, clusters, even us. But for now, in this part of the story, we rest in stillness. Atoms have arrived, and the cosmos has become a place where vision is possible. Now that the universe is transparent, now that light has found its wings and atoms have found their partners, you might imagine a peaceful, ordered cosmos taking shape all at once. Galaxies blooming like flowers, stars flickering into life like campfires in the dark. But not yet. What we have now is vastness, a sea of hydrogen and helium drifting softly through an ever-expanding space. There's no light other than the fading glow of the cosmic microwave background. No stars, no planets, just atoms and the quiet. It's a beautiful silence, but beneath that stillness something remarkable is beginning. You see, the early universe wasn't perfectly smooth. It was almost smooth. Almost, but not quite. Tiny ripples were imprinted into the fabric of space itself, seeded by quantum fluctuations magnified during inflation, that rapid stretch of space just after the Big Bang. These weren't dramatic waves. They were tiny, variations in density so slight, so subtle, that you might compare them to the difference between a quiet breath and a whisper. But gravity, patient, unsentimental gravity, noticed. In the denser spots, atoms began to gather, just slightly more than average, enough to make a difference over time, and then those differences grew. It was the beginning of structure. Like flour slowly settling into patterns on a kitchen counter, the atoms started to drift together. Some areas became denser, some emptier. Over millions of years, these clumps would grow, slowly pulled tighter by gravity, fed by their own increasing weight, like puddles turning to rivers. But the visible matter, what we call normal atoms, wasn't doing this alone. Something else was helping. Something we couldn't see, and still can't. Something that doesn't shine, doesn't absorb, doesn't scatter light at all. Dark matter. It may sound ominous, but dark matter is simply matter that doesn't interact with light the way normal atoms do. We know it's there, not because we can see it, but because of how it tugs, how it bends gravity, how it guides the motion of galaxies and the shape of the universe itself. Dark matter formed its own scaffolding, an invisible web stretching across the cosmos. Into this web, normal matter flowed like dust into cracks, settling into the patterns laid down by this unseen force. Galaxies would one day form along its filaments, clusters at its intersections. Even now, billions of years later, the large-scale structure of the universe still echoes this early blueprint. But back then, there were no stars yet to light it up, no fire in the darkness. The atoms were just beginning to gather, like guests arriving early to a party that hadn't quite started. It would take time, hundreds of millions of years, but eventually gravity would do what it always does. It would pull enough atoms together, press them tight, ignite fusion, and stars, at long last, would be born. But in this moment, we are still in the fog. Not the hot, glowing fog of before, but a cooler, invisible one. A kind of dark age. A time when the universe was full of matter, full of potential, but waiting. Quietly. And in that quiet, everything was already in motion. And now we arrive at the threshold. The atoms have formed. The fog has cleared. Gravity has begun to gather quiet clouds of hydrogen and helium into loose, drifting pockets. It's been hundreds of millions of years since the Big Bang, a span of time that feels impossibly long to us, but for the universe it's still early morning. What we see now is a cosmos made mostly of hydrogen, the simplest element, a single proton with a single electron, just enough to be called an atom, just enough to begin shaping everything. Helium floats nearby, made from 2 protons, 2 neutrons, and a surrounding veil of electrons, a little more complex, a little more reserved. Together, hydrogen and helium make up 99% of the normal matter in the universe. No carbon yet, no oxygen, no iron or gold or silicon. Just these 2 quiet elements, waiting patiently for their chance to become something more. This is a universe not of fire and fury anymore, but of potential. The energy that once boiled everything apart has stretched and cooled. The light that once danced violently now drifts calmly through space, a gentle echo of brighter days. And the atoms, tiny, invisible, tireless, are moving, gathering, preparing. You could imagine this era like a great cosmic stillness, but beneath that stillness is momentum. Hydrogen clouds collapse slowly under their own weight. Some drift for millions of years before anything happens. Others begin to press inward, particle by particle, their gravity pulling tighter with every breath of time. And eventually, when the pressure grows high enough, when the temperature inside these clouds climbs beyond imagination, something ignites. Fusion. Atoms begin to fuse together, releasing light, heat, and the signature of a newborn star. We'll talk about that more in the next part of our journey, but for now, just pause here, in this newly open universe, the one that can finally build. Because structure doesn't come from chaos alone. It needs quiet. It needs calm. And the atoms, those same hydrogen and helium atoms formed from the first light, are finally free to move and bond without constant interference. They're like architects, patiently laying the first bricks in a long, slow blueprint of complexity. It's strange to think about, isn't it, that from two basic elements, one unimaginably simple, the other just slightly less so, the entire universe will unfold. Stars, planets, oceans, trees, music, conversation, breath. You are, in many ways, a story told by hydrogen, shaped by its partnerships, illuminated by its fusion, anchored by the helium that cooled the stars and softened the light. This is the beginning of that story. From here, we'll travel into the fire, into the hearts of the first stars where atoms will begin to change, where hydrogen will become helium again, but also carbon, oxygen, and the entire library of elements that makes everything familiar. But that is next. For now, let's sit with a simplicity, with a universe just beginning to shape itself, with atoms that are no longer scattered, but purposeful, no longer adrift, but assembling, a universe that can now build. Let's return now to the quiet universe we left behind, filled with hydrogen and helium, adrift in the wake of clarity. No galaxies yet, no colours, no metals, no chemistry, just cold, calm gas drifting through the dark, but not forever. The silence is about to break, not with noise, but with light. In certain places where gravity was patient and firm, hydrogen clouds have been gathering for millions of years. These aren't small puffs of gas. They're massive, enormous. Clouds so big they make planets look like dust. Inside them, gravity begins to compress the hydrogen atoms, slowly at first, then faster. As the atoms are squeezed tighter, their temperature rises tens of thousands, then millions of degrees, until finally in the densest part of the cloud the atoms give in. They fuse, and with that, the first stars are born. These are the population 3 stars, a term astronomers use for the very first generation. They're unlike any stars you can see in the night sky today. Formed from pure hydrogen and helium, untouched by heavier elements, they are thought to be colossal, perhaps 100 times the mass of our Sun, or even more. Because of their size, they burn bright, and they burn fast. Where our Sun might last 10 billion years, these giants may have lived only a few million, a cosmic heartbeat, and then gone. But during their brief lives, they performed one of the universe's first true transformations. Inside their cores, hydrogen atoms were fused into helium. This is the same fusion our own Sun carries out today, but in these ancient stars the process was more intense, driven by enormous pressures and temperatures. Fusion is what powers a star. It's what gives it light, and it's what begins to reshape the universe's atomic menu. These stars are the first true furnaces of matter. They took the simplest element, hydrogen, and turned it into something more. And though they couldn't make heavy elements yet, they set the stage. They seeded the cosmos with light and motion, turning quiet clouds into active regions where future stars would form. And when these early stars died, they didn't just fade, they exploded. But we'll come to that soon. For now, picture one of these ancient stars. A giant blazing quietly in a universe that had never known such light. No planets yet to orbit it, no eyes to see it. Just a sphere of fusion, floating in the void. A signal fire in the darkness. Every atom in your body, your calcium, your iron, your oxygen, depends on what happened inside and after these stars. Without them, There would be no you, no forests, no music, no memories. These were the stars that lit the way, and their light still echoes. The first stars came and went like sparks in a wind, but they left behind something profound, a universe now ready to craft new stars, built not just from hydrogen and helium, but also from the faint traces of heavier elements those early giants released. And with this second generation of stars, something new begins. Something extraordinary. The quiet shaping of the periodic table. This process, known as stellar nucleosynthesis, is how stars become the universe's blacksmiths. Not by hammer or fire, but by the steady pressure of gravity and the slow glow of fusion. Inside a star, atoms are not fixed. They change. They combine. They transform. Let's take a look inside. At the heart of a star, hydrogen is being fused into helium. That's where it begins. But in larger stars, ones more massive than our Sun, the temperatures rise even higher. The pressure deepens, and new layers of fusion awaken. Helium begins to fuse into carbon. Then carbon fuses with helium to form oxygen, and neon, then magnesium, then silicon. The process continues in nested shells, like layers of an onion, each one burning hotter than the one before. The star becomes a kind of celestial engine, forging elements step by step. A cosmic forge, reshaping the universe one atom at a time. Eventually it reaches iron, and there, it stops. Iron is different. Unlike the fusion of lighter elements, which releases energy, fusing iron requires energy. It doesn't pay the universe back, it drains it. So when a star's core fills with iron, the process halts. No more fusion, no more outward pressure to counter gravity. The balance collapses, and in that collapse the star's fate is sealed. But let's stay here for a moment, at the edge of iron. Think about this. The iron in your blood, the same iron that helps carry oxygen through your body, was once at the centre of a dying star. A star that burned for millions of years, layering elements like stories in a book. Until finally, it could go no further. And yet, that end was only a new beginning. Because iron, while marking the death of a star, also sets the stage for a spectacular rebirth. In the moments following the collapse, during what comes next, all the elements beyond iron, gold, uranium, platinum, are formed, but not through fusion, through explosion. We'll get there soon. But even before that final burst, stars have already given us a stunning gift. Carbon, oxygen, nitrogen, calcium, all born in stellar cores, then scattered into space. Stars don't just shine, they build. And in doing so, they transform a simple universe into one that's rich with possibility. A universe where, one day, atoms could form molecules, and molecules could dream. Every star, no matter how bright, no matter how enduring, has a moment when it can no longer hold itself together. It begins quietly. The fuel runs low, the fusion slows, the outward pressure that held gravity at bay begins to falter. And in that silence, gravity speaks louder. For smaller stars, like our Sun, the ending is soft. The outer layers drift away in glowing waves, forming delicate shells of gas called planetary nebulae. The core, no longer burning, shrinks into a white dwarf, a hot, dense ember glowing softly for billions of years, slowly cooling, never fusing again. These stars don't go out with a bang. They sigh into stillness. But for larger stars, the ending is something else entirely. When a massive star builds up a core of iron, it reaches a crisis. Iron doesn't fuse. It doesn't give back energy. So the star has no way to resist its own weight. In a fraction of a second, the core collapses. Atoms are crushed. Protons and electrons are squeezed into neutrons, releasing a flood of neutrinos. The collapse slams to a stop, rebounds outward, and then explosion. A supernova. It's one of the most violent events in the universe. In those brief, searing moments, the star outshines entire galaxies. The shockwave rips through the star's outer layers, tearing atoms apart, fusing new ones, scattering elements into space. And in that furnace of chaos, the universe forges what even stars could not. Gold, uranium, cobalt, lead. The heaviest elements born not in life, but in death. It's a kind of cosmic recycling, destruction as creation. The remains of the star depend on its size. Sometimes the core stabilizes as a neutron star, an object so dense that a teaspoon of it would weigh more than a mountain, a place where atoms no longer exist as we know them, just a solid mass of neutrons packed shoulder to shoulder. But if the star is even more massive, gravity doesn't stop, it keeps collapsing. Past the neutron state, past any known matter, until it forms a black hole, a region where gravity is so strong not even light can escape, a place where atoms are no longer just rearranged, they're erased from ordinary space. And yet, even in these strange remnants, these corpses of stars, the story of atoms continues. The elements flung out by supernovae will drift through galaxies. They'll mix with gas clouds. They'll fall into new stars, and some of them will end up in rocks, in rivers, in cells. You carry atoms that were once inside exploding stars. Some were forged in their death throes, others in quieter fusion fires. They travelled for billions of years to find you, to become your bones, your blood, your breath. So yes, the death of stars is violent, but it's also generous, because in dying, stars don't just end, they share, and through that sharing everything else becomes possible. After the brilliant flash of a supernova fades, after the last shreds of the dying star drift into the quiet again, something subtle begins, a kind of scattering, a spreading, a slow drifting ballet of atoms finding new homes. Because when a star dies, it does not simply vanish. It leaves behind its gifts. All those heavy elements forged in its core, or in the explosion itself, don't stay put. They're hurled into the surrounding space, flung outward in every direction, carried by shockwaves and starlight. Iron, oxygen, carbon, calcium, gold, atoms that didn't exist before, now float freely in the interstellar dark. They cool, they condense, they drift. This is cosmic recycling, and it never stops. Those atoms, now free from the star that birthed them, become interstellar dust. Not the kind of dust you brush off a bookshelf, but particles so fine, so small, that trillions could float through a teacup without you noticing. And yet, they matter, because they are the raw material for everything to come. Over time, this dust joins with the ever-present hydrogen and helium. Gravity, always watching, starts to pull them together. Again and again, across the galaxy, clouds form. Some clouds drift for millions of years, quiet and undisturbed. Others bump gently into each other, merging like sleepy dancers, and still others swirl into tight spirals, pressed inward until, once more, stars are born. But these new stars are different. They aren't made of just hydrogen and helium anymore. They are richer, touched by stardust, infused with heavier elements, and around them, in the swirling disks of leftover matter, the conditions are now just right for something wonderful to begin. Planet formation. Planets don't form from nothing. They need rock, ice, metal, materials that only exist because of the stars that came before. Without that dust, there would be no soil to grow in, no oceans to sail, no hands to hold. And so the atoms continue their journey. An oxygen atom, once trapped inside a giant star, now cools within a comet, waiting patiently at the edge of a solar system. A carbon atom, forged in fusion, finds itself embedded in the leaf of a tree. A calcium atom rests in the enamel of a tooth. None of these atoms remember where they came from, but they've all travelled far, and they are used again and again. That's the beauty of the universe. It doesn't waste. Every atom gets a second chance, a third, a thousandth, passed from one form to another, from one life to another. The same iron that once flowed through the heart of a star might now flow through yours. The gold in your ring, the potassium in a banana, the oxygen in your breath, none of them were born on Earth. They were brought here, long ago, by the generous death of stars. So when we speak of cosmic recycling, it's not just poetic, it's personal. You're made of recycled stardust, atoms borrowed from fire and returned to stillness, atoms that may one day be part of something else, a mountain, a moon, a heartbeat not yet imagined, and all of it still moving, still drifting, still ready to build something new. Let's drift now toward the calm edges of a newborn star. It burns brightly at the centre, young, restless, full of energy. But surrounding it is a wide, swirling disk, a soft spiral of gas and dust made from the leftovers of its own birth. Hydrogen, helium, carbon, iron, bits of atoms flung outward during collapse and now caught in orbit. This is where planets begin. Not all at once, not cleanly, but slowly, quietly, over time. You might imagine this disk as a cosmic kitchen counter dusted with flour and sugar. Nothing sticks at first, but given time, pressure and motion, things begin to clump. Tiny grains of dust collide. Most bounce off, some stick. Those that do become the seeds of something larger. Grains become pebbles, pebbles become rocks. Rocks gather into boulders, then planetesimals, small growing bodies just big enough to attract other things with their own gravity. This is accretion, the slow, persistent pull of matter toward a more matter. It's not dramatic, it's not loud, but it works. Over millions of years, these scattered atoms come together, bit by bit, building the first planets. Some stay small, asteroids, comets, moons. Others grow massive, collecting not just rock, but gas, becoming the gas giants. Jupiter, Saturn, worlds of swirling clouds and liquid metallic hearts. And then there's a small rocky one. Not too big, not too small, just the right distance from its star. Rich in iron, wrapped in carbon, veined with oxygen. We call it Earth. But before it had blue oceans or green forests, Earth was a molten sphere. Violent, constantly bombarded by leftover debris. Volcanoes hissed, lava rolled, and still the atoms continued their work. They cooled, they layered. Iron sank to the core, lighter materials floated upward, a crust formed, atmospheres brewed, water arrived, perhaps carried by icy comets from the outer reaches, or released from deep within the planet's rocky mantle. And through it all, atoms rearranged themselves. Oxygen joined hydrogen to form water. Carbon linked with oxygen to form carbon dioxide. Silicon and oxygen bonded into minerals. Slowly, the surface became stable enough to hold oceans, to form continents, to cradle air. This wasn't chance. It was chemistry guided by gravity. Time steered by the patience of atoms. The planet didn't choose its elements. They were gifted to it, delivered by stars long gone, gathered through collisions, shaped by heat and pressure. The Earth is not a separate thing from the stars. It's their quiet continuation. Even now, the ground beneath your feet is an arrangement of ancient atoms. The calcium in your bones once floated in space. The potassium in a banana was born in a star. The iron in your blood may have come from a supernova that died before Earth even existed. When you hold a rock, you are holding time. When you breathe, you are breathing stardust. And all of it, the land, the air, the sea, was built through this patient process, accretion. The slow gravity-driven gathering of atoms into something steady, something solid, something alive with possibility, a planet. And on that planet, something else is about to begin. Now the Earth is cooling. The fires have quieted, the crust has hardened, the air is thick but present. Water pools in low places gathering into early oceans, the sky swirls with clouds, rain falls, thunder rumbles, and all around something gentle begins, chemistry. not in laboratories, not in flasks or beakers, but in warm puddles, bubbling vents, and mineral-rich mud. On this early Earth, the atoms that travelled from ancient stars start to bond, not just by proximity, but by affinity, by the quiet pull of electrons searching for balance. Chemistry is the art of atoms finding partnership. It starts with simple combinations. Hydrogen bonds with oxygen to form water, a molecule so basic, so vital, it becomes the foundation of nearly everything else to come. Carbon bonds with itself, creating chains, rings and webs. Nitrogen links in, creating compounds that store energy, carry information, catalyse reactions. No single molecule shouts, but together they hum. In these early reactions, covalent bonds dominate, where atoms share electrons like neighbours borrowing sugar, like hands reaching out and deciding to hold. These bonds are stable, but flexible. Strong, but not unbreakable. The perfect balance for building something that can change. And change they do. Tiny molecules assemble into larger ones. Chains of carbon, loops of phosphate, spirals of sugar. These are not alive. Not yet. But they are ready. They're complex enough to hold meaning, to carry patterns, to spark reactions in return. You might think of this stage as a quiet rehearsal. The atoms are trying things out, binding and unbinding, drifting and settling. The chemistry is messy, yes, but it's purposeful. It's curious, it's searching, and the environment helps. Lightning cracks through the sky, energizing the soup. Sunlight pours through clouds, splitting molecules apart so they can rejoin in new ways. Deep under the sea, thermal vents puff mineral-rich water into darkness, warm, sheltered pockets where reactions happen in peace. Everywhere, atoms are rearranging. This is the dawn of organic chemistry, the chemistry of carbon-based molecules, the kind that make up life. Not life itself, but its alphabet. The building blocks of membranes, enzymes, genetic material. Molecules that can copy themselves. Molecules that respond to heat, light, acidity, and time. And still, no spark of awareness, no heartbeat, no hunger or thought. But the ingredients are there. The instructions are beginning to write themselves. What began in the core of stars is now beginning again. This time, not as fusion, but as connection, as pattern, as memory in molecular form. It's easy to overlook chemistry. It doesn't shine like stars. It doesn't echo like supernovae. But without it, atoms remain alone. Without it, life cannot begin. So we linger here for a moment, with the molecules in the mud, the swirling soup of early Earth, the quiet pond where water meets stone, and time waits patiently. This is where the universe becomes not just matter but possibility, and soon, from that possibility, life will rise. Now that atoms are gathering into molecules, and molecules into more complex patterns, we pause to appreciate something often overlooked: bonding. Not the dramatic kind you find in novels, or the instant attraction of magnets snapping together, but the quiet, patient way that atoms decide to stay, linked not by force but by balance, by the give and take of electrons, by a kind of gentle commitment. There are different ways atoms bond, and each one has its own personality. The most familiar, perhaps, is the covalent bond. This is the sharing kind. Two atoms come together and pool their electrons in a mutual space. Neither dominates. They build something together, stable but not rigid. Think of water. Two hydrogen atoms and one oxygen, each sharing their electrons to create a molecule that is far more than the sum of its parts. Then there's the ionic bond, a bond of transfer. One atom gives up an electron, another takes it. The resulting charges, positive and negative, hold them together like static cling. It's a bit more possessive, a bit more polarised, but it works. Table salt, for instance, sodium and chlorine, held together not by gentle sharing, but by the electricity of difference. And then there's the metallic bond found in the hearts of metals. Here, atoms release their outer electrons into a shared sea, allowing them to move freely. It's this free-flowing electron ocean that gives metals their shine, their flexibility, their ability to conduct heat and electricity. The atoms are fixed, but the electrons roam like a city of lanterns, each glowing from a shared current. Each bond is a different kind of relationship. Each allows for different structures, different behaviours, different forms of beauty. And beauty does emerge. Carbon, for instance, forms some of the most versatile bonds in the periodic table. It can link with itself in chains, branches, rings, and spirals. It can connect to oxygen, nitrogen, hydrogen, sulfur, building molecules of staggering complexity. Proteins, sugars, DNA. Carbon is the social butterfly of the atomic world. Always reaching, always connecting, always trying new configurations. But even the simplest bonds matter. They are what allow matter to have texture, tension, shape. They are why soap dissolves grease, why ice floats on water, why breath carries warmth. They give the world structure, from the chalky shell of a snail to the clear lenses of your eyes. When you sip a warm drink, when you pick up a stone, when you hug someone you love, what you're really feeling is bonding, molecules interacting, electrons dancing at the edge of contact. And these bonds don't just hold matter together, they hold memory. The shape of a protein determines its function. The folding of DNA holds the instructions for life. Even a single bond in the wrong place can change everything. There's something tender in that the world doesn't need huge forces to shape it, just tiny agreements between particles, just patterns that hold, and when atoms bond, they don't stop being themselves. Hydrogen stays hydrogen, oxygen stays oxygen, but together they become something more, something useful, something stable, something that, over time, might even think. All of life, all of motion, all of chemistry is built on these invisible handshakes, these quiet, loyal dances between atoms. Molecular love stories unfolding every second. From the soft tides of Earth's early oceans, from warm pools and rocky shores, something extraordinary begins to stir. It doesn't happen all at once. There's no flash, no trumpet, no moment of sudden awareness. Life doesn't appear like a switch being flipped. Instead, it emerges, slowly, gently, like mist rising from a quiet pond. And behind it all, the atoms continue their quiet work. The chemistry that's been bubbling for millions of years begins to arrange itself into patterns that last. Molecules that were once random now start to copy themselves. Some fold in just the right way to attract others. Some curl into loops that carry information. Some link together, forming membranes that keep the outside world out, and the inside world safe. These are not yet cells, not fully, but they are steps towards something organised, something persistent, something alive. One of the great players in this transformation is the amino acid, a simple molecule made from carbon, hydrogen, nitrogen and oxygen. There are many types, but together they form proteins, long folded chains that act like tiny machines. Some bend into keys, others into hinges or cups or arms. Their shapes determine their function. They don't just sit there, they do things. Another player is RNA, a single-stranded cousin of DNA. It's capable of carrying instructions, of copying itself, clumsily, imperfectly, but enough to continue, enough to evolve. Eventually, these molecules learn to work together. Encased in protective bubbles, primitive membranes, they begin to divide, they begin to change, they begin to pass on information to the next version of themselves, and suddenly the atoms are no longer just drifting, they're participating. From stardust to seawater, from random motion to memory, the universe has taken a long, slow breath and breathed out life. It's not intelligent yet. It doesn't have eyes or thoughts or dreams, but it grows. It adapts. It learns in the way molecules can learn, by failing, by mutating, by surviving what came before. What began as hydrogen in the heart of a star is now becoming structure in the strand of a gene. Atoms that once floated in silence are now telling stories, coded in base pairs, folded into proteins, whispered through generations of replication. And eventually, from these earliest forms come cells, bacteria, algae, ferns and fungi, creatures that crawl, swim, fly, eyes that look back at the stars, hands that write, minds that wonder, all from atoms. It's strange to think that something so small could carry so much, that a few electrons, a few protons arranged just so, could lead to curiosity, to memory, to music. But that's the quiet miracle of life. It didn't require magic, just time, atoms, and the right conditions to say yes to each other. And here you are, listening to this story, breathing in oxygen that came from a tree, built by atoms that came from stars, built in fact by the very same processes we've followed all along. Atoms fused in fire, shaped in death, recycled, rebonded, remembered, and now they're you. Let's shrink ourselves now. We've spent so much time drifting among stars, swimming in oceans of light, tracing the travels of atoms across galaxies. But now we step inward, into the heart of those atoms, into the space where nature begins to whisper instead of shout. At first glance, an atom seems simple, a nucleus at the centre made of protons and neutrons, and around it, electrons, tiny, swift, orbiting like planets around a sun. But this picture, while familiar, is not quite right. The reality is stranger, softer, less certain. Let's start with the electromagnetic force. Protons are positively charged, electrons are negatively charged. Opposites attract. That's why electrons are drawn to the nucleus, pulled inward by the quiet tug of charge, like a moth toward a lantern. And yet, they don't crash into the nucleus. They don't spiral inward like comets falling into the sun. Why? Here's where things become beautifully strange. Electrons are not little balls, not really. They're more like waves, or perhaps clouds. They don't have precise positions. They exist in a haze of possibility, described by quantum mechanics, a set of rules so gentle and bizarre that even after a century of study it still feels dreamlike. Electrons are drawn inward by the nucleus, yes, but they are also pushed outward, not by force, but by quantum constraint. They can't just be anywhere. They can only exist in specific energy levels, defined distances from the nucleus where their wave patterns fit perfectly, like the ringing of a bell. Too close, and the pattern breaks. Too far, and they lose the tug. Only at these sweet spots can they truly settle. And these orbits aren't like planetary tracks. They're more like clouds of probability, shapes where the electron is likely to be, but never guaranteed. It's not circling. It's not spinning. It's existing in a delicate state of maybe. So we end up with something stable but strange. An electron constantly pulled inward, but unable to fall because the rules won't allow it. This balance between electromagnetic attraction and quantum restriction is what keeps atoms from collapsing. It's a kind of quiet tug of war, not one of struggle, but of harmony. The charge says, "Come closer." The quantum laws reply, "Only this far." And so the electron stays, floating, bound, not spinning in circles, but resting in possibility. This is the structure that underpins everything you see. Your chair, your skin, the steam from a kettle, all made of atoms held together by these silent agreements. So the next time you hold something, anything, know that its existence depends on tiny charges pulling and tinier rules preventing collapse. That the object feels solid only because of a balance happening far beneath your touch. In the next sessions we'll move deeper into the nucleus itself, where another kind of force does its quiet work. But for now, we rest here, just outside the core, with electrons floating in their invisible patterns, each one held, each one bound, each one staying. Now let's step further inward, past the electrons, through the soft haze of probability and into the nucleus. This is where protons and neutrons reside, packed tightly together in the heart of the atom. It's easy to imagine them sitting calmly, side by side, but there's a quiet mystery here, one that, at first glance, doesn't make much sense. You see, protons are all positively charged, and like charges repel. That's a basic rule of electromagnetism. Two positive charges don't like to be near each other. They push apart. So, why doesn't the nucleus fly apart? How can a cluster of protons stay so close, sometimes dozens of them, without the whole thing bursting apart in a shower of repulsion? The answer is one of the most powerful, most mysterious and most important forces in the universe, the strong nuclear force. Unlike gravity, which acts at large distances, or electromagnetism, which works across atoms, the strong force is tiny in range. It only works inside the nucleus. But within that tiny space, it is incredibly powerful, strong enough to overcome the repulsion between protons. It acts like a kind of atomic glue. The strong force holds protons and neutrons together. In fact, it doesn't care much about charge. It binds both. What matters is closeness. If two particles are within the right distance, about the size of a nucleus, the strong force pulls them together so tightly that even their natural repulsion can't break them apart. At this level, we meet the smallest known building blocks, quarks. Protons and neutrons aren't indivisible. They're made of quarks, bound together by particles called gluons. Gluons are the messengers of the strong force, constantly flitting between quarks, carrying the binding energy that keeps them together. It's hard to picture, because we're now in a world where distance is measured in femtometers, a millionth of a billionth of a meter. But even here, structure exists, patterns hold, stability is possible. This balance between repulsion and nuclear cohesion is why atoms can exist at all. Without the strong force, there would be no stable nuclei, just a universe of scattered protons forever flying apart. You might think of the nucleus as a crowded room full of people who don't get along. They'd push and shove, trying to get away. But if someone strong enough came in and held their hands gently, just tightly enough, they'd stay. Not because they want to, but because something deeper is holding them in place. That's what the strong force does. It doesn't erase repulsion. It just outmatches it. Quietly, locally, completely. And yet, this force is not limitless. If you try to pack too many protons into one nucleus, the repulsion starts to win. That's why large atoms like uranium are unstable. They're balancing too much push and not enough pull. In those atoms, the strong force begins to lose its grip, and when that happens, we get radioactivity, a topic we'll gently approach in the next sessions. But for now, let's sit with this strange and silent force. It's the strongest of the four fundamental forces in nature, but it doesn't reach far. It's hidden deep inside everything, doing its work invisibly, holding together the parts of you, of stars, of all matter. And in that invisible closeness, the universe finds its core, not loud, not visible, but unwavering. In the quiet heart of the atom, alongside the pushy protons and the electromagnetic tension they bring, there lives a quieter companion, the neutron. At first glance, the neutron seems like a side character. It has no charge. It doesn't attract or repel. It doesn't light up the atom like electrons, and it doesn't crowd the nucleus with the same drama as the protons. And yet, the neutron is essential. Without it, atoms would fall apart, stars would misbehave, chemistry would crack. Life, as far as we know, wouldn't exist. Let's take a closer look. The neutron's most important role is to add stability. Remember, protons all carry a positive charge, and like charges repel. That means any group of protons packed into a nucleus is under constant stress. Like magnets all forced to touch north to north. It's the strong nuclear force that holds them together, as we've seen, but that force works best at just the right spacing. That's where neutrons come in. They act as spacers, buffers. They slip between the protons, easing the repulsive forces while still contributing to the strong nuclear binding. They make the nucleus more comfortable, more balanced. Without them, even the strong force would have trouble keeping things from bursting apart. Think of it like this. A group of siblings in a small room might bicker if left alone too long. But if a quiet cousin sits between them, calm, neutral, it helps everyone get along. That's the neutron. Different atoms need different numbers of neutrons to stay stable. Hydrogen, for instance, usually doesn't need any. It has only one proton, so there's nothing to repel. Helium, with 2 protons, needs 2 neutrons. But as atoms get heavier, they need more and more neutrons to offset the growing crowd of protons. And when that balance is off, when there are too many or too few neutrons, things start to become unstable. That's where radioactivity comes in. Unstable nuclei don't like being imbalanced. They look for ways to fix themselves. Sometimes they emit a neutron. Other times they convert one of their neutrons into a proton, or vice versa, through a process called beta decay. These changes are sudden, energetic and transformative. It's a bit like a chair trying to stabilise itself by rearranging its legs mid-sit. Not always graceful, but often effective. And sometimes the imbalance is too great. The nucleus can't fix itself and it simply breaks apart, releasing particles, heat and radiation. That too is part of the neutron story. We'll explore it more in the next session as we gently unfold the idea of isotopes and decay. But for now, let's return to the stillness of the stable nucleus. In atoms like carbon-12, oxygen-16 and calcium-40, the number of protons and neutrons is just right. These nuclei don't decay, they don't emit, they just are. Balanced, lasting, tranquil at the core. And the neutrons, still there, still quiet, still working. It's easy to overlook the neutron. It doesn't call attention to itself. It carries no charge. It moves silently within the nucleus. But without it, the atom is unstable. Without it, the dance of chemistry collapses. So the next time you think of matter as solid and reliable, remember the quiet stability of the neutron, the unseen peacekeeper inside every atom, a whisper of balance, a keeper of calm. Let's now turn our attention to one of the atom's quiet secrets, the idea that not all atoms of the same element are exactly the same. Meet the isotope. Take carbon, for instance. Every carbon atom has 6 protons. That's what makes it carbon. But not every carbon atom has the same number of neutrons. Some have 6, forming the stable carbon-12. Others have 7, forming carbon-13, also stable. And a few rare ones have 8 neutrons. Carbon-14, which is unstable. These variations are isotopes, atoms of the same element with different neutron counts. The same identity but slightly different mass, and often different behaviour. Most isotopes are stable. They exist quietly, holding their balance, but some are not. Some isotopes are radioactive, meaning they're prone to change. They decay, sometimes slowly, sometimes quickly, into other elements or forms, releasing energy in the process. This decay is not violent, not explosive. It's more like a sigh, a quiet reshuffling inside the nucleus. A neutron becomes a proton, or vice versa. A particle slips away. A bit of heat escapes. This process is called radioactive decay, and it comes in many forms. Alpha decay, where the nucleus sheds 2 protons and 2 neutrons, a helium nucleus. Beta decay, where a neutron turns into a proton, or a proton into a neutron, releasing an electron or positron. Gamma decay, where excess energy is released as a photon, pure light. Each decay follows its own rhythm, and together these rhythms shape how long an isotope lasts. That brings us to the idea of a half-life. the time it takes for half of a sample of radioactive atoms to decay, not all at once, not predictably, but statistically, on average. It might be a second, it might be thousands of years. But the pattern holds, and that pattern allows us to measure time. You've probably heard of carbon dating, a technique used to determine the age of ancient bones, wooden tools, and forgotten campfires. It works because carbon-14, the unstable isotope, is created in Earth's atmosphere and taken in by living things. While we're alive, we keep refreshing our supply by breathing and eating. But once something dies, the carbon-14 begins to decay, no longer replaced. By measuring how much carbon-14 remains, scientists can calculate how long it's been since that living system stopped renewing itself. A soft atomic clock, ticking silently through centuries. Radioactive decay doesn't just tell time, it also saves lives. In modern medicine, certain isotopes are used to target cancer cells, highlight tumours, trace blood flow. Tiny amounts of radioactivity, carefully chosen, offer insight and healing. We call it nuclear medicine, but really it's the gentle use of an atom's natural rhythm. Of course, not all radiation is helpful. Too much exposure can damage cells, mutate DNA, interfere with the delicate instructions that life depends on. That's why we treat radioactivity with caution, because it's powerful, and because it acts on levels too small to see, yet too important to ignore. Still, there's a strange beauty in it. Atoms, restless and imbalanced, seeking a quieter form, transforming over time, not destroyed, just changed, just like stars, just like you. Each isotope a tiny story of identity and impermanence, a reminder that even atoms evolve, that even at the smallest scales time has texture, weight, meaning. And in that slow decay, the universe keeps a kind of memory of what was, of what is becoming. Let's return now to the edge of the atom, where electrons live, but not in tidy orbits, not in fixed paths, like planets around a star. That image, while comforting, is a kind of simplification, a postcard from an older view of physics. The truth is stranger, softer, more dreamlike. Electrons don't move in circles. They exist in patterns of probability. They don't follow a path. They occupy a cloud. This is the world of quantum mechanics, and it's not something we can easily picture. Because electrons don't have definite positions when left alone. They're described by wave functions, mathematical patterns that tell us where the electron is likely to be, not where it is. Think of it like fog around a mountain peak. The thicker the fog, the more likely you are to find the electron there. But you'll never know its exact location, only its likelihood. These probability patterns are called orbitals, and they come in different shapes, spheres, dumbbells, rings, and more complex forms. Each shape corresponds to a different energy level and electron configuration. The simplest orbital, the one closest to the nucleus, is shaped like a soft, fuzzy ball. Others bloom outward, with lobes and petals, like quiet origami in invisible space. Electrons move between these orbitals, but only in quantum leaps. No smooth slides, just sudden changes, discrete jumps from one state to another, releasing or absorbing energy in the process. That's where the glow of a neon sign comes from, or the subtle flash of a firefly, or the inner workings of the stars. Electrons leaping between energy levels, exchanging light for motion, or motion for light. And underpinning all of this is the uncertainty principle, a rule that says the more precisely we know an electron's position, the less we can know about its momentum, and vice versa. It's not about faulty instruments. It's not about imprecision. It's a fundamental truth. Nature is fuzzy at small scales. Reality at this level is a blend of possibility and limitation. This might sound chaotic, but it's not. It's beautifully predictable in its own way. These clouds of probability form reliable shapes. They obey strict rules. They fill the space around atoms in layers, like the rooms in a house, where only a certain number of guests can gather in each room, and each room must fill before the next can open. And this structure, this quiet, foggy architecture, is what gives the periodic table its rhythm. It's why elements behave the way they do, why oxygen loves to bond, why helium doesn't, why metals conduct and carbon builds chains. Every solid, every liquid, every gas is built on these shimmering clouds. So the next time you imagine an atom, don't picture marbles in motion. Picture a mist of possibility, a whisper of presence. An electron isn't in a place, it's likely to be there. It's a softness, not a dot. And yet, from that softness comes solidity. The table, the air, the water, your skin, all built on clouds that never collapse, waves that never fully resolve, particles that only exist when the universe allows them to be known. This is not illusion. It's not vagueness. It's the foundation of all form. Reality, not as fixed lines, but as shimmering possibility. You might wonder, as you drift deeper into this invisible world, how atoms can exist at all. With electrons pulled inward by the nucleus's electric charge, with no clear walls to hold them back, why doesn't everything just collapse inward, squeezed into nothingness? Why don't the electrons fall into the nucleus like rain into a drain? The answer lies in one of the most quietly powerful ideas in all of physics, the Pauli exclusion principle. Named after physicist Wolfgang Pauli, this principle tells us that no two electrons can occupy the same quantum state. That is, no two electrons in an atom can share the exact same energy level, position, and spin. It's like an invisible set of rules for a very exclusive hotel. Each room can only hold one guest of a certain kind. Once a state is taken, no one else can move in, not even if they try. The electrons are not allowed to collapse into the same lowest energy level. They must find their own space, their own arrangement. And this is why atoms have structure. Why electrons fill shells and orbitals in layers. Why the periodic table has its familiar rows and columns. Each electron must follow the rules, like dancers keeping just enough distance to avoid stepping on each other's toes. This quantum refusal to overlap gives atoms their size. It creates volume from nothing more than force and principle. But there's another quiet actor at play, zero-point energy. Even in their lowest allowed state, electrons never truly come to rest. They still buzz, wiggle, hum, not from external energy, but from the very nature of quantum space. This is zero-point motion, the smallest, gentlest movement allowed by the universe. Not noise, but a fundamental whisper of presence. And because this motion can never fully stop, the atom can never fully shrink. There's always a floor, an irreducible baseline of movement, even at absolute zero, even in the coldest, darkest, most isolated corner of the cosmos. In this way, atoms are like restless sleepers. Even when they lie still, they shift slightly. They breathe at the edge of possibility. They never collapse, not because they resist, but because they can't. The laws of physics gently forbid it, so matter holds its shape. The desk, the blanket, the bones in your hand, they don't dissolve into the centre of their atoms, even though gravity and charge pull inward constantly. They hold because of refusal, because of structure without contact. You've never seen the Pauli exclusion principle. You've never felt zero-point energy directly. But you're surrounded by them, shaped by them, held upright because of them. Even white dwarfs and neutron stars, those strange stellar remnants we met earlier, are held up by these same ideas. A white dwarf resists further collapse because the electrons inside it are obeying the exclusion principle. They've run out of space. The matter becomes degenerate, not in a moral sense, but in a physical one, packed so tightly that no more compression is allowed. Atoms don't collapse because they cannot, because nature builds in limits, boundaries of being, and from those boundaries comes form. There's a chart you've likely seen many times, on classroom walls, in science books, hanging quietly in laboratories and lecture halls, the periodic table of elements. It might look like just a grid of numbers and symbols, H, he, Li, B, B, and so on. Tidy boxes in even rows and staggered columns. But this chart is more than a reference. It's a map of atomic behaviour, a kind of cosmic calendar, a blueprint of the universe's building blocks, written in the language of electrons. Each element in the table is defined by its atomic number, the number of protons in its nucleus. That number also tells you how many electrons it holds when it's neutral. And those electrons, as we've explored, don't just sit anywhere. They fall into structured shells, layers of energy levels governed by the rules of quantum mechanics. The first shell holds 2 electrons, the next 8, then 18, and so on. But it's not just about how many electrons there are, it's about where they're placed. This is why the table has groups, the vertical columns where elements share similar chemical behaviours. The elements in group 1, like hydrogen and sodium, each have a single electron in their outermost shell. That makes them reactive, eager to lose that one electron and stabilise. On the far right, in group 18, you'll find the noble gases, helium, neon, argon. Their outer shells are full, which makes them reluctant to bond with others. They're content, complete, the quiet observers of the chemical world. In between are all the characters of the periodic drama, alkaline earth metals, halogens, transition metals, metalloids, each family with its own habits, preferences, and affinities. Some give electrons easily, others hoard them. Some form delicate bonds, others forge sturdy chains. And this organisation isn't arbitrary. It flows from the very structure of the atom, from how electrons occupy their spaces, and how those spaces influence behaviour. It's a kind of patterned dance, one shaped not by aesthetics, but by fundamental rules. The periodic table is the choreography of matter. It tells you, at a glance, which elements are likely to combine, which will spark, which will rust, which will glow. It tells you why water forms the way it does, why salt crystals shape themselves into cubes, why carbon can be soft as graphite or hard as diamond, depending on how its atoms are arranged. Even the colours of stars are written here. Blue giants, red dwarfs, yellow suns. They all burn with different shades because of the elements they contain, and how those elements' electrons absorb and emit light. The periodic table isn't just a list, it's a map of possibilities, and it's still growing. New elements, synthesized in labs, fill the final rows, unstable, short-lived, exotic. They live for fractions of a second before decaying. But even in their brief existence, they obey the same rules, fit into the same map, like rare visitors, arriving just long enough to say, the pattern still holds. So next time you glance at that quiet grid, remember, it's not just decoration, it's a cosmic chart, a record of how atoms build, behave and bond, a whisper of the logic beneath the chaos. It's the universe's index of matter, and it begins with hydrogen, the first and simplest atom, the one born from the Big Bang, the one that started it all. We often think of atoms as static things, small, precise building blocks that sit neatly in place, like marbles in a jar or bricks in a wall, unmoving, predictable, still. But the truth is gentler, stranger, and somehow more beautiful. Atoms are never truly still. Even in the coldest corners of the universe, even in the quietest room, atoms move. They vibrate, they oscillate, they dance. Every particle inside them, every electron, proton and neutron shifts ever so slightly. Not out of clumsiness, but because the universe itself won't allow complete rest. This movement is subtle, invisible, but it's always there. In solids, atoms wiggle in place, like people in a crowded elevator adjusting their footing ever so slightly. In liquids, they slide past each other, bumping gently, swirling softly. In gases, they drift far and wide, carried by temperature and chance. Even at absolute zero, the coldest possible temperature, Where all thermal energy is meant to vanish, motion doesn't stop completely. Because of zero-point energy, quantum mechanics demands that some jitter remain, that the particles still hum faintly as if whispering to themselves in the dark. And it's not just the atoms that move. Their electrons are in constant quantum flux, flickering between energy states, orbiting in probability, their positions unknowable but never meaningless. Protons and neutrons within the nucleus also shift, tugged by the strong force, held in balance, but still pulsing with energy. This motion is not chaos, it's not instability. In fact, it's the opposite. This constant motion is what creates stability. If particles were frozen, if electrons stopped moving, if atoms went perfectly still, they would lose the very properties that define them. The structure of matter would collapse, chemistry would halt, light wouldn't flow, life couldn't begin. Stability, it turns out, is not about staying still. It's about moving in harmony. Atoms don't need to freeze to hold their shape. They need to cooperate, to vibrate within boundaries, to shift within patterns, to remain in motion without losing their integrity. This is what makes materials flexible. It's what lets a metal bend without breaking, what allows water to flow but still hold its form, what lets your skin stretch and return. At every scale, the world is built on motion that doesn't unravel. Even thermodynamics, the science of energy and heat, rests on this principle. When you heat something, you're not adding colour or weight, you're adding movement. Atoms jiggle faster, bonds stretch and rebound more vigorously. At high enough temperatures, those bonds break and matter changes state, from solid to liquid, from liquid to gas. But none of it is wasted. The energy is simply translated, shared, redirected, dissipated. And even as things cool down, as atoms calm, as motion slows, structure remains. The world doesn't need frenzy to hold itself together. Just enough motion, just enough balance. So when you sit quietly in your room, in the hush of night, it may feel like everything around you is at rest. But beneath the surface, atoms are moving, calmly, steadily, persistently. And that movement is what allows the world to feel solid beneath you, to hold you, to be familiar. It's a kind of paradox, isn't it? That everything we touch is built from things that never truly touch. That solidity is an illusion born from movement. That permanence is just a dance that doesn't end. And in that dance, gentle, timeless, invisible, we find the secret rhythm of reality. If you lift your hand and hold it quietly in the light, you might see only skin, wrinkles, maybe a freckle or a scar. You might think of it as yours, part of your body, part of your story. But look deeper. That hand is made of atoms. Carbon, mostly. Also, oxygen, hydrogen, calcium, and nitrogen. Some iron, phosphorus, traces of others. Elements scattered across the periodic table, now gathered into cells, skin, blood and bone. But where did those atoms come from? Not from your parents, not from food, at least not originally. Their story stretches much farther, because long before they became you, these atoms were something else. They were stardust. The carbon in your bones was forged in the furnace of a dying star. The oxygen in your lungs came from a supernova's brilliant death. The iron in your blood was created in one of the universe's most violent explosions, an event so energetic that it forged the heaviest elements and flung them across space. Billions of years ago, a massive star reached the end of its life. It had spent its youth fusing hydrogen into helium, then helium into heavier elements. Carbon, neon, oxygen, silicon. Finally it created iron, and with that the star could no longer hold itself up. It collapsed, and then it exploded. That explosion scattered its elements into the galaxy. Those atoms drifted, they wandered. For millions of years they floated between stars, part of great clouds of gas and dust. Eventually gravity gathered those clouds again. New stars formed. Around one of them, a small yellow star in a quiet spiral arm, planets began to form. And on one of those planets, life began. Those same atoms passed down through rock, water and plant, eventually entered food, breath and cell. And now, they are you. You're not metaphorically made of stars. You are literally made of stars. The nitrogen in your DNA, the phosphorus in your bones, the calcium in your teeth, the iron that helps your blood carry oxygen. Every part of you was once part of something ancient, explosive and vast. And still, those atoms are calm, quiet. They're not glowing or buzzing or burning. They've found new form, new purpose. They've slowed from their wild, stellar past into the rhythm of metabolism, thought, and rest. Your body is a temporary arrangement of ancient materials, a soft collection of borrowed pieces. And one day those pieces will return to the soil, the sky, the sea, ready to become something else. This is the humbling magic of atoms. They don't belong to us. They only pause with us. They travel through time, not with memory, but with structure. Through stars, planets, plants, animals, and now through you. They're old beyond imagining, and yet here they are forming something that thinks, dreams, wonders. So when you look at your hand again, try to see through the surface, past the veins and fingerprints, past the skin and sinew, see the atoms, and know they came from fire, and now they are part of you. Once inside you, atoms don't stay in place. They move, gently, quietly, persistently. They're exchanged with every breath, every bite of food, every drop of water. The body is not a sealed container, it's a passing place, a temporary residence in a larger living network. Let's follow 3 of these elemental wanderers: carbon, nitrogen, and phosphorus, each one essential, each one always on the move. Not randomly, but as part of a vast, elegant pattern. This is the circulation of elements, the Earth's soft choreography. Take carbon. You exhale it with every breath, not as solid, but as carbon dioxide, a gas, invisible but important. That gas floats into the air where plants absorb it through their leaves. With sunlight and water they turn it into sugar, photosynthesis, a quiet miracle repeated trillions of times a day. When you eat plants, or something that ate a plant, that carbon enters you. It's used to build cells, fuel energy, form molecules. Some of it stays, some of it returns to the air with your next breath. This is the carbon cycle, a loop of life and air, of eating and exhaling, of light becoming leaf, becoming limb, becoming life again. Now meet nitrogen. It makes up about 78% of the air you breathe, but you can't use it directly. It's locked in a form too stable, too inert. To become useful, nitrogen must be fixed, broken apart and recombined by bacteria in the soil or by lightning in the sky. Once transformed, it enters the roots of plants, then moves up into stems, leaves, fruit. Animals eat it. You eat them or the plants they ate. Now nitrogen helps build your proteins, your DNA, the instructions inside every one of your cells. When you shed skin, when leaves fall, when life ends, nitrogen returns to the soil, and the bacteria begin again. The nitrogen cycle is subtler than carbon's, less visible, more reliant on life's smallest partners, but just as essential. And then there's phosphorus. Unlike carbon or nitrogen, phosphorus doesn't float through the air. It comes from rock, from minerals worn down by water, cracked by frost, dissolved by roots. Plants absorb it, animals consume it. In you, it becomes part of your bones, your teeth, your cells' energy system. You couldn't grow without it, couldn't think, couldn't heal. When organisms die, phosphorus returns to the soil, to lakes, to oceans. There it settles, waits, and over long spans of time becomes rock once more. The phosphorus cycle is slow. Centuries may pass between its journeys, but it is no less vital. Together these cycles form a kind of planetary breath. Atoms are passed from one being to another, not owned, only borrowed. The air that feeds the trees feeds you. The soil that feeds the grain becomes part of your muscles. When you return those atoms to the earth, they become part of something else, a fox, a fern, a mountain daisy. And so, life is not a series of separate stories, but one long, continuous exchange. Ecosystems are not just collections of animals and plants, they are vast systems of atomic choreography. The same carbon atom that built a leaf may someday help build a heartbeat. The nitrogen from a raindrop may find its way into a poem, and phosphorus, quiet and patient, might pass from bone to root to sky. Nothing is lost, everything circulates. Take a breath. In. Outside. It feels simple, effortless, but behind that breath is a quiet cascade of chemistry. With each inhale, you're not just filling your lungs with air, you're inviting atoms in. Most of them are nitrogen, yes, but tucked within every breath is something special: oxygen. This oxygen is not passive, it's active, curious, hungry for electrons, and because of that, it's the centerpiece in one of the most elegant exchanges in all of life: cellular respiration. Let's begin with what happens after you eat. The food you digest, carbohydrates, fats, proteins, is broken down into smaller molecules. These molecules carry stored energy, harvested from the sun by plants or from other animals. But to use that energy, your cells need to release it. They do so not with flame, but with a slow, controlled burn. Oxygen, brought in through breath and carried by the blood, arrives in the cell. There, inside tiny structures called mitochondria, it meets electrons released from food molecules. Through a series of careful steps, those electrons are handed along a chain of molecules, each one capturing just a bit of the energy. This is aerobic respiration, a process of burning without fire. At the end of the chain, the electrons meet oxygen, which combines with hydrogen to form water. The entire exchange releases energy, which your cells store in little molecular packets called a TP, fuel for movement, thought, healing and growth. It's easy to forget that this is combustion, in essence. But it is, just not the kind that scorches. It's a gentle burn contained within the walls of your cells, happening trillions of times a second. Now compare that to fire, the roaring visible kind. When wood burns, it's undergoing combustion too. Heat breaks the bonds between atoms in cellulose and other organic compounds. Oxygen rushes in, binding with carbon to form carbon dioxide, with hydrogen to form water vapour, releasing light and heat in the process. Both fire and breath do the same thing. They oxidize fuel, they rearrange atoms, they release energy. But fire is fast and uncontrolled. Breath is measured, purposeful, alive. One destroys, one sustains. It's a quiet wonder that the same process that lights a forest fire also powers your heartbeat, that the atoms in a flame are behaving in the same fundamental way as those in your cells. Oxygen doesn't choose one or the other. It only follows the rules, seeking electrons, forming bonds, releasing energy. The difference is in the context. In fire, atoms let go all at once, tumbling into new configurations in a flash of heat. In respiration, they pass from one molecule to another like notes in a song, carefully timed, never rushed, building energy that life can hold. And both leave behind the same marks: carbon dioxide, water, and warmth. So the next time you take a breath, think of it as an invitation. You're calling in the same oxygen that fuels stars and flames, asking it not to rage but to serve, to help you move, heal, remember, and rest. And in the exhale, you release the story back into the air, ready for a tree or a flame or another breath to begin again. Inside nearly every cell of your body, nestled within a quiet core called the nucleus, sits a story. Not written in ink or spoken in language, but shaped in atoms, arranged into molecules, patterned into instructions. This is your DNA. It isn't flashy. You can't feel it working. But it's there, coiled and folded like a delicate ladder, several billion steps long, tucked into a microscopic space. And every rung of that ladder is made of atoms in conversation. Let's look closer. DNA is built from 4 basic building blocks: adenine, A, thymine, T, cytosine, C, and guanine, G. These are called nucleotide bases, and each is a molecule made from carbon, nitrogen, oxygen, and hydrogen. Familiar elements, arranged in very particular ways. Always pairs with T, C, always pairs with G. This pairing is more than just chemistry. It's a kind of molecular agreement, a code that ensures your cells know how to grow, repair, and function. The order of these bases, their sequence, is what matters. It's like a sentence made not of letters, but of atoms in structure. One stretch of bases might instruct a cell to build a protein that carries oxygen. Another might guide the development of your eyes. Another still might sit quietly, unused, part of an older instruction long retired. And it's all made possible by chemical bonds. Hydrogen bonds hold the base pairs together, gentle enough to unzip when needed, strong enough to stay aligned. Covalent bonds link the backbone, a steady chain of sugar and phosphate groups that form the spiral rails of the double helix. These aren't just physical structures. They are the very logic of life. When a cell divides, it copies its DNA. The strands unwind, and each half serves as a template. Free-floating bases in the nucleus find their matches, forming new strands, step by atomic step. Mistakes sometimes happen. A base is missed. A bond breaks. But often, other molecules step in to correct it. Your cells are full of these quiet caretakers, enzymes that edit and maintain the molecular script. It's a process both precise and forgiving, resilient yet flexible, and all of it is built on carbon's generosity, its ability to form 4 stable bonds, to hold hands with many partners, to create rings and chains and branches. Carbon is the author. Oxygen and nitrogen help shape the syntax. Phosphorus connects the structure, hydrogen softens the grip, and somehow from this assembly of quiet elements, a living narrative emerges. DNA doesn't think, but it stores, and by storing it guides, and by guiding it creates. You, every eyelash, every heartbeat, every memory, written in atoms, copied, read and reread by cells too small to see. Their machinery silent, their loyalty complete. And it's not just humans. Trees, birds, jellyfish, mushrooms. Each one carries its own molecular story. Different words, same alphabet, same language of shape and bond. A shared chemistry whispered across. Billions of years. So when you think of identity, think of this. You're not a single thing. You're a pattern held in matter, a song written in carbon, a living paragraph that stretches from your ancestors to your children to whatever comes after. Your atoms didn't write the story, but they carry it faithfully, and they always have. Close your eyes for a moment. Notice what happens, not just the dark behind your eyelids, but the thoughts that continue to rise. Memories, sensations, perhaps the awareness of your body on the bed, the rhythm of your breathing, the comfort of stillness. All of that, every thought, every flicker of sensation, is made possible by atoms moving across membranes. The whispers of charged particles, a quiet electric ballet inside your brain and nerves. This is not the kind of electricity that powers your lamp or heats your tea. This is biological electricity built on ions, sodium, potassium, calcium, slipping across the walls of your cells. Let's begin with a neuron, a single nerve cell. At rest, it holds a delicate imbalance. More positive ions outside the cell, more negative ions inside. This difference is maintained by little protein pumps, constantly shuffling sodium out and potassium in. It creates potential, a kind of invisible tension, like a coiled spring. And when the time comes, when a message must be sent, a tiny channel opens, sodium rushes in, the imbalance shifts, that tiny change triggers the next channel to open, and then the next. Like a line of falling dominoes, this wave of shifting charge travels down the neuron. It's called an action potential, and it's how signals move from one end of your body to another. No wires, no motors, just ions, responding to movement and charge. When the signal reaches the end of the neuron, it doesn't leap across the gap to the next one. Instead, something gentler happens. The arrival of the signal causes calcium ions to enter the cell. This triggers tiny bubbles, vesicles, to release molecules called neurotransmitters into the space between cells. These molecules float across the tiny gap and bind to receptors on the next neuron, continuing the message. And all of this happens in milliseconds, over and over, across trillions of connections. It's how you see, how you move your hand, how you remember a name, hear a song, feel warmth on your skin. But remember, it's not the neurons doing this alone, it's the atoms. Sodium, potassium, calcium, common elements, not rare or mysterious, coordinating something breathtaking. Their size is minuscule, but their role is immense. Their presence shapes your awareness. Their flow becomes your thoughts. And what's more, your brain is always changing. With each repeated thought, connection, or sensation, the strength of these atomic signals can increase or fade. That's how memory forms, how habits are built, how healing happens after injury. A kind of atomic plasticity, a rewiring of who you are, shaped by the flow of ions and the bonds of molecules. You're not a static blueprint. You're an ever-shifting pattern of charged particles, arranged with care, responding to life. The atoms in your thoughts were once part of water or stone or fruit. Now they move with purpose, guiding muscle, voice, imagination. And they do, it all without consciousness. They don't know they're part of something called you, but you do. And that awareness, that gentle, self-reflective noticing, is built on their silent motion. Your body, though it may feel familiar and unchanging, is never the same from one moment to the next. The atoms that make up your muscles, your skin, your organs, they don't stay. They come, do their work and move on, quietly, gently, without ceremony. You're a process, not a statue, a river of atoms, not a stone. Consider your skin. It sheds and renews itself constantly. Every few weeks your outer layer is replaced, the old cells flaking off as dust, while new ones rise from below. The atoms in those cells come from food you ate, air you breathed, water you drank. The lining of your stomach too is rebuilt often, its cells worn down by the acids they produce and quietly replenished, atom by atom, molecule by molecule. Your bones, though harder and slower, are alive as well. They break down old material and deposit new, keeping themselves strong and responsive. Even your blood is renewed. Red cells last just a few months before being dismantled and replaced. They're iron recycled. So while your sense of self may feel continuous, your body is more like a moving mosaic, always changing pieces but maintaining the shape. It's estimated that most of the atoms in your body today weren't there a decade ago. Even your skeleton, the part of you that seems most permanent, has traded many of its atoms for new ones, and still, you are you. That's the quiet miracle. Identity through change. A pattern held in flux. A form that remembers itself, even as its parts are replaced. But this replacement isn't always perfect. Over time, the machinery of repair begins to wear. DNA copies with slightly more error. Cell division slows. Proteins misfold a little more often. The balance between breakdown and rebuilding begins to shift. This is aging, not a single event, but a gradual tipping of scales. It's not the atoms that age. Carbon is just as stable at 5 billion years as at 5 seconds. Oxygen doesn't tire. What changes is how well your body coordinates the use of those atoms, the efficiency of repair, the subtle loss of perfect balance. And yet even aging is beautiful in its way. It's a reflection of life lived, of sunlight absorbed, of meals shared, of laughter and memory and breath. Each wrinkle, each line, is a record of time's passage through your biology, and healing, though slower with age, never fully stops. A cut still closes, a bone still knits, cells still rally, atoms still answer the call. There is a kind of grace in knowing that the material of your being is borrowed, rebuilt constantly, and yet arranged just so to be you. You're not the same person, physically, that you were 10 years ago. But the pattern has held, the story continued, the atoms changed, but the self endured. Not fixed, but familiar. Like a flame that shifts and flickers, yet always carries the same light. Eventually all patterns come to rest. The breath quiets, the cells stop dividing. The rhythms of metabolism slow, then cease. This is death, not the disappearance of matter, but the release of arrangement, the ending of a particular story told in atoms. But the atoms themselves, they do not die, they do not vanish, they are not damaged by the stillness, they remain. Once, they were part of you, a liver cell, a strand of hair, a memory. But now, they begin their next journey, leaving the organised pattern of a living body and returning to the wider world. Enzymes break apart molecules. Bacteria arrive, each one a tiny engine of disassembly. The barriers between systems dissolve. Boundaries soften. What was once you becomes part of something else. Some atoms return to the air exhaled as gases. Some sink into the soil, drawn into roots, pulled upward by trees. Some wash into rivers, then oceans. Others settle into rock. A fox might walk by, nibble a leaf, and take in a carbon atom you once carried in your skin. That atom may one day help it run, or stretch, or curl up beneath the stars. Nothing is lost. Even in decay there is continuity. This is not a tragedy. It's the closing of a loop, the fulfillment of a promise, that atoms never truly belong to anyone. They only pause, gather, shape, and then move on. The same nitrogen that once helped form a thought may become part of a flower. The calcium from your bones might help form the eggshell of a bird you'll never see. And on the cycle turns. In this way, death is not an ending, it's a return to the earth, a return to the elements, a return to the possibility of new forms, new stories, and your atoms, so old, so well travelled, will continue. They may drift through clouds, rest in stone, or rise again in the stem of a sapling, in a grain of wheat, in the lungs of a child yet unborn. You are not gone, you are changed. The pattern you were has finished. But the pieces of that pattern remain in motion, quietly, calmly, becoming something else. And perhaps, when the wind brushes past a field, or when the ocean takes in a quiet breath, some small part of you is there, moving forward endlessly, without fear. Everything fades, not suddenly, not with a bang, but with a soft drift, a slow surrender. The stars burn out, the warmth spreads thin, the patterns begin to loosen. Atoms, too, those resilient little building blocks, eventually face change they cannot resist. Not all at once, but gradually, steadily, with time as their only enemy. Let's begin with radioactive decay, a kind of quiet undoing. As we've seen, some atoms are unstable. Their nuclei have the wrong mix of protons and neutrons. They try to fix this. A neutron becomes a proton, or a cluster of particles escapes. The atom becomes something else, more stable, less strained. This decay releases energy, sometimes softly, sometimes with great force. But once the transformation is complete, the atom rests in a quieter state, less reactive, less hopeful, just still. It's easy to think of decay as destruction, but really, it's a kind of settling, the release of tension, the return to simplicity. Beyond radioactive elements, other structures also wear down. Molecules break apart, bonds weaken, heat, the random motion of atoms, rattles them loose. Left alone, complex arrangements unravel, not in malice, but in accordance with entropy, a soft rule that favours disorder over order, spread over concentration. A steaming cup of tea grows cold, not because the heat vanishes, but because it spreads. It diffuses into the room, the walls, the air. The once focused warmth becomes gently uniform until no gradients remain. No difference to drive motion, just calm. This is the essence of the universe's projected fate, heat death. It sounds dramatic, but it's not fire or explosion. It's the opposite. It's equilibrium, a final state where everything has evened out, where all usable energy has been spent, no more stars forming, no more planets glowing. Just matter and radiation, evenly distributed, too smooth to change. It's a kind of cosmic silence. But we're not there yet. The universe is still bustling with movement, star birth, reaction, and collapse, still rich in contrast. But entropy, the soft pull toward stillness, works patiently. It does not rush, it simply waits. And as it waits, it rearranges. It breaks the links between atoms, spreads them further apart, dilutes energy, until even light finds no gradients to follow. Until even time, in a sense, becomes indistinct, because without change, how can time be measured? It's not something to fear. It's not something we'll witness. It's a story told in trillions of years, unfolding far beyond the scale of lifetimes or even civilizations. But it reminds us of something important, that all forms are temporary, all structures are pauses in the greater flow, that being solid, alive, organized, it's a privilege, a rare arrangement, and all arrangements eventually dissolve, even the atom, even the warmth of your hand, even the stars. There is a place where atoms go not to scatter but to vanish, where gravity doesn't just pull, it overwhelms, where space bends beyond repair and time itself begins to twist, a place where the rules we trust begin to whisper something stranger. This is the domain of the black hole. Born from the death of massive stars, black holes are the end result of gravitational collapse. When a star runs out of fuel, it can no longer push outward against the crushing pull of its own mass. If it's heavy enough, the core falls inward, past atoms, past protons, past even the known structure of matter, into a point of infinite density called a singularity. At that centre, everything that falls in, light, matter, information, reaches a place where known physics no longer speaks clearly. And the boundary around that place, that's the event horizon, a silent, invisible sphere where escape becomes impossible. Not because something holds you in, but because space itself curves inward so steeply that all paths lead down. If you tossed an atom into a black hole, just a single, lonely hydrogen atom, it wouldn't bounce. It wouldn't disintegrate in flames. It would simply fall, quietly, forever. As it approaches the event horizon, something strange would happen. From an outside perspective, the atom would appear to slow, to stretch, to fade, its information smeared across the horizon like a ghost. Inside, it would be gone, folded into the singularity, compressed beyond shape. This is gravitational destruction, not in fire but in folding. The atom's structure can't resist the pressure. The forces that held its protons and neutrons together are overwhelmed. The strong nuclear force, once unbreakable, is now insufficient. All form is lost. And this leads us to a puzzle that has stirred physicists for decades, the information paradox. In quantum mechanics, information, meaning the arrangement of particles, the history of interactions, is supposed to be preserved. Nothing, it says, is ever truly forgotten. But when something enters a black hole, that information seems to disappear, evaporated, erased. If the black hole later evaporates via Hawking radiation, the outgoing particles appear random, bearing no trace of what fell in. So where did the information go? Some believe it's encoded on the surface of the black hole like a cosmic hologram. Others think it's released in some subtle, scrambled form as the black hole fades. Some even suspect that our understanding of space-time and matter is still missing a vital piece. But for now, we don't know. Black holes are mysteries of finality. They erase structure, stretch atoms beyond recognition, and raise the quiet question, can the history of a thing ever truly be lost? Perhaps not. Perhaps the universe remembers, just not in ways we yet understand. But in the meantime, black holes remain a kind of cosmic punctuation mark, a full stop at the end of certain atomic stories. Not loud, not fiery, but deep, silent, and absolute. There is a place where atoms go not to scatter, but to vanish, where gravity doesn't just pull, it overwhelms, where space bends beyond repair and time itself begins to twist. A place where the rules we trust begin to whisper something stranger. This is the domain of the black hole. Born from the death of massive stars, black holes are the end result of gravitational collapse. When a star runs out of fuel, it can no longer push outward against the crushing pull of its own mass. If it's heavy enough, the core falls inward, past atoms, past protons, past even the known structure of matter, into a point of infinite density, called a singularity. At that centre, everything that falls in, light, matter, information, reaches a place where known physics no longer speaks clearly. And the boundary around that place, that's the event horizon, a silent, invisible sphere where escape becomes impossible. Not because something holds you in, but because space itself curves inward so steeply that all paths lead down. If you tossed an atom into a black hole, just a single, lonely hydrogen atom, it wouldn't bounce. It wouldn't disintegrate in flames. It would simply fall, quietly, forever. As it approaches the event horizon, something strange would happen. From an outside perspective, the atom would appear to slow, to stretch, to fade, its information smeared across the horizon like a ghost. Inside, it would be gone, folded into the singularity, compressed beyond shape. This is gravitational destruction, not in fire, but in folding. The atom's structure can't resist the pressure. The forces that held its protons and neutrons together are overwhelmed. The strong nuclear force, once unbreakable, is now insufficient. All form is lost, and this leads us to a puzzle that has stirred physicists for decades, the information paradox. In quantum mechanics, information, meaning the arrangement of particles, the history of interactions, is supposed to be preserved. Nothing, it says, is ever truly forgotten. But when something enters a black hole, that information seems to disappear, evaporated, erased. If the black hole later evaporates via Hawking radiation, the outgoing particles appear random, bearing no trace of what fell in. So where did the information go? Some believe it's encoded on the surface of the black hole like a cosmic hologram. Others think it's released in some subtle, scrambled form as the black hole fades. Some even suspect that our understanding of space-time and matter is still missing a vital piece. But for now, we don't know. Black holes are mysteries of finality. They erase structure, stretch atoms beyond recognition, and raise the quiet question, can the history of a thing ever truly be lost? Perhaps not. Perhaps the universe remembers, just not in ways we yet understand. But in the meantime, black holes remain a kind of cosmic punctuation mark, a full stop at the end of certain atomic stories, not loud, not fiery, but deep, silent, and absolute. We've talked about what atoms are, how they come together, how they shape stars, trees, thoughts and blood. But now, let's look forward, far forward, beyond memory, beyond Earth, beyond even the last star. What happens to atoms in the end? The short answer is they last for a while, but not forever. Hydrogen atoms, the simplest, most abundant form of matter, have already lasted nearly 14 billion years. The carbon in your bones, the oxygen in your breath, the iron in your blood, these atoms will outlive you. They will outlive your descendants. They will outlive the sun. But there is a horizon even they cannot cross. It begins when the stars go out. In the far future, star formation will slow and eventually stop. The hydrogen fuel runs low, the lights dim, one by one stars burn out, becoming white dwarfs, then black dwarfs, cold, dark, dense remnants. These will last for quadrillions of years, but even they will cool and fade. With no new stars forming, galaxies grow dim. The universe enters what scientists call the degenerate era, an age ruled by embers, black holes, cold stars, faint flickers of atomic activity. Even then, atoms still persist, lonely, sparse, moving slowly. But then comes the deeper question. Will even protons decay? This is still unknown. But some theories in physics suggest that protons, the building blocks of atomic nuclei, may not be eternal. They might have a half-life, so long we've never observed it, stretching 10 to the 34 years or more. If this is true, then every atom is on borrowed time. Bit by bit, protons would break down into smaller particles, radiation, a soft flicker of nothingness. Electrons too might eventually fade or be absorbed into black holes as they evaporate, and if all of that happens, what remains? No stars, no planets, no atoms, just radiation. Thin, low-energy photons drifting through an enormous, empty and cold cosmos. This is sometimes called the Dark Era, an epoch not of darkness like night, but of absence. No light, because there's nothing left to shine. No structure, because the particles that once formed things are gone. Just faint echoes, endless space, and time without clocks. Still, even in this, there's something strangely peaceful. The universe, having burned and built and blossomed, rests. Atoms, for all their longevity, were only one chapter. A long one, yes, but not the last. And what's most humbling is that we live in a time of atomic richness. A time when atoms still gather, still dance, still write poems and power thoughts. We're here during a thin, rare slice of time when matter holds its shape. We are part of the brief golden age of atoms, and though the future may seem cold, even lonely, it is not a tragedy. It is simply the long exhale of something vast, ancient and complete. A quiet settling, a final pause. And even in that stillness, the memory of form will remain, in the faded echo of every atom that once was. Nothing lasts forever, not even atoms. But that doesn't mean anything is truly lost. It only means that everything changes. There's a quiet grace in that idea, a softness to it, the way a snowflake melts, not into nothing, but into water, into movement, into something new. The structure dissolves, yes, but its substance remains, and atoms follow the same path. They begin as quarks and energy, pulled from the fire of the Big Bang. They build protons and neutrons, gather electrons, become hydrogen and helium. In stars, they fuse into heavier elements. They drift through nebulae, become part of rocks, rivers, skin, and thought. They don't choose their path, but each step is a kind of invitation to participate in the next thing. When a living thing dies, its atoms don't mourn. They rearrange, return to the soil, rise in roots, settle into wind. Maybe rest in the shell of a beetle or the curve of a seashell. They don't disappear. The atom doesn't need memory to persist. It simply is, carried forward by time and transformation. And in this there is no waste. Even decay is a form of belonging to a longer, wider pattern. The carbon in your cells once lived in trees and stones. The iron in your blood once flowed in the heart of a star. The atoms in your breath may someday help form the wings of a moth. The patterns shift, but nothing is thrown away. And that's true for you too. Your story, the particular arrangement of you, may one day dissolve. The specific neural dance that forms your memories, your voice, your smile, those things may fade, but the matter will remain. The ingredients will continue. They will take new shape, follow new rhythms, and somewhere in that new form a small trace of you persists, not as a self, but as a contribution, a presence that became part of something else. Nothing lasts, but nothing's wasted. This is the quiet reassurance of the cosmos, that even endings have their place, that even the unravelling is part of the weave. We don't often see it this way. We grow up with stories that favour permanence, castles, names, legacies carved in stone. But the universe offers a different comfort, that impermanence is not failure. It's motion, it's participation, it's freedom. Even the stars, those beacons of light we see scattered through the night, will end. They will burn out, collapse, or fade, but their atoms will not be lost. They will become something else. You too are part of that same cycle. You're made of matter that has never been destroyed, only passed along, gifted, reused, renewed, and when your pattern ends, the atoms will continue, so nothing is truly gone. It's only elsewhere now. So now, let's pause. Let's sit quietly with everything we've gathered, with the birth of atoms from the Big Bang, their fusion in stars, their journey into dust, then breath, then blood, and finally, their quiet release back to the cosmos. And in the middle of all that, you, made of atoms. It sounds simple, but it isn't. To be made of atoms is to be shaped by forces older than time as we know it. It is to carry matter forged in the cores of stars, refined through eons of pressure and fire, and gently passed into this moment, into this body, into this thought. Because yes, even your thoughts are made of atoms. The neurons that fire, the ions that flow, the molecules that build and break, all of them built from the same carbon, hydrogen, nitrogen, oxygen that you'd find in a leaf or a cloud or a comet. You're not separate from the universe. You're not above it or outside of it. You're within it, a part of it that, for a time, can observe itself, reflect, wonder, whisper questions into the dark. You're a pattern, yes, but one held in matter. And this pattern is remarkable not just for what it does, but for how long it took to arise. For billions of years, atoms did not think. They spun and collided and fused. They built stars, broke them apart. They formed molecules, then oceans, then cells. And at some point, those cells began to carry memory, then sensation, then something more. Now, here you are, reading, thinking, feeling. You're the latest chapter in a story that began before there were even pages. A momentary arrangement of particles that allows the universe to reflect on its own existence. And yes, one day this pattern will fade. The atoms will move on. They'll return to soil or air or sea. They'll stop echoing with your thoughts and begin echoing with something new. But while they are here, or while they are you, they carry something precious. The capacity for wonder. The ability to feel awe at the stars or comfort in the warmth of another hand. To laugh, to love, to imagine. That is what it means to be made of atoms. Not just to be built, but to be animated, aware, alive. And when the time comes for your atoms to scatter again, they will not mourn. They will remember only through transformation, through motion, through the soft promise that nothing is wasted. But for now they hold together. For now they rest in you. A breath in the universe, a question, a pause, and perhaps that is more than enough. Nature doesn't rush, but it remembers. You can see it in a snowflake, 6 arms unfolding from a single centre, each branch repeating the other, shaped by temperature and moisture, but always rooted in the rules of water's atomic form. That shape isn't arbitrary. It begins with a single oxygen atom, holding hands with 2 hydrogens, forming a gentle V. And because of the way water molecules connect, bonding through attraction, angle and charge, they arrange themselves into hexagonal lattices. What begins as invisible geometry becomes a snowflake drifting through the air, cold, delicate, brief, and unique, but only in its details. Its foundation is pattern, and patterns like this are everywhere. Crystals form because atoms prefer order when they settle. If given the time and space, they align into tidy grids. That's why salt forms cubes, and quartz forms 6-sided columns. It's not about beauty, it's about energy. The lowest energy configuration is often the most symmetrical, but beauty seems to follow close behind. You'll see it in a sunflower spiral, in the arrangement of a pine cone, in the curve of a shell. These are not conscious choices. They are echoes of the golden ratio, a quiet numerical harmony that seems to emerge wherever growth meets efficiency. At the atomic level, this harmony is written in repetition. How atoms bond, how molecules twist, how proteins fold. It's not forced, it simply happens. You might not think of a coral reef or a nautilus shell as mathematical, but they are. Each layer, each ripple, is the result of molecules arranging themselves in predictable yet intricate ways. A dance of atoms that produces spirals, curves, ridges. Even your own body follows this rhythm. The spiral of your fingerprint, the branching of your veins, the double helix of your DNA. Patterns, rooted in atoms, echoed in form, and artists for centuries have echoed them back. From Islamic tiles to Gothic cathedrals, from fractal paintings to golden ratio sketches, human hands have traced what molecules quietly assemble. We build what we feel as balanced, often because atoms built it that way first. The boundary between science and art softens here. When you admire a piece of lacework or a frost-covered window pane, you're seeing atomic behaviour scaled up, form born from repetition, complexity born from simplicity, and always, beneath it all, stillness. Atoms aren't rushing to make beauty. They simply settle where forces guide them, and in that settling, pattern arises. Form appears, a snowflake, a shell, a sonnet. So next time you look at something and think, that's beautiful, pause a little longer. You might be seeing atoms at rest, and in that stillness, they've quietly written something elegant. We often think of time as something outside ourselves, a ticking clock, a calendar on the wall, a sunrise, a sunset. But beneath all these markers, beneath the hands that sweep and the bells that chime, there is something even more constant, something smaller, more precise. Atoms. Atoms don't just build the world, they measure it too. At the heart of this truth is a simple idea. Certain atoms, when nudged just right, vibrate at perfectly consistent frequencies. So consistent, in fact, that we've come to trust them more than anything else to keep track of time. This is how we define a second. Not by the swing of a pendulum or the movement of the sun, but by the cesium atom. A silvery element you'll rarely think about, but which quietly governs the rhythm of your life. In an atomic clock, a beam of cesium atoms is passed through a magnetic field. Inside, scientists look for a specific transition, an electron jumping from one energy level to another. And this jump, it occurs exactly 9,192,631,770 times per second. That number isn't rounded. It isn't an estimate, it's the very definition of a second. When your phone tells you the time, when a GPS satellite orbits overhead, When stock markets trade in microseconds or rockets launch with millisecond precision, they're all trusting the atom's steady beat. Atomic clocks are so accurate that they would lose or gain only about a second in 100 million years. And we use them not just to count seconds, but to shape entire systems. GPS satellites carry atomic clocks because even a tiny drift, just a few billionths of a second, would translate into meters of error on the ground. To map your location accurately, we rely on atoms that never forget to tick. But the connection goes deeper than just machinery. Your body responds to atomic rhythms too. The day-night cycle, the changing seasons, they affect hormones, sleep, temperature, even thought. And while you may not have a cesium clock inside your chest, you have something just as faithful: molecular cycles. Proteins rise and fall in predictable patterns. Genes switch on and off at set times. Neurons fire in rhythmic waves. These patterns, your circadian rhythms, are synchronized not just by sunlight, but by the very timing of molecules assembling and breaking down. Atoms, it seems, carry both the structure and the tempo of your life. And yet, they feel so still. They don't hum or tick. They don't move in ways you can see. But in their silence, they mark the passing of everything. Stars age, hearts beat, dreams begin and end, all in step with the reliable, invisible movements of atoms. So time, perhaps, isn't something far away. Not something you chase or fall behind. It's within you, built into the very particles that form your breath, your bones, your thoughts. Each second you experience is born from the same structure that builds stars and snowflakes. That's the quiet gift of the atom. It gives you a body, yes, a mind, a world, but also a rhythm. Before the sun rises, before your eyes open, your body already knows it's time to begin again. You may not feel it, but deep inside you, a quiet cascade has already started. Molecules begin to shift. Hormones stir. Neurons nudge each other awake. Your body is preparing, not just to move, but to align with the world beyond your skin. This is rhythm, not the kind you hear in music, but the kind that hums in every cell. And at its heart, atoms. Let's begin with your heartbeat. It's steady, though it speeds and slows depending on your needs. At its core is a patch of cells called the sinoatrial node, your natural pacemaker. These cells generate electrical signals, and those signals ripple across your heart muscle, telling it to contract. But how do those cells know when to fire? Inside them, atoms are at work. Sodium, potassium, and calcium ions shift across cell membranes in tightly timed sequences. Their movement creates tiny voltage changes, electrical rhythms born from atomic shifts. With every beat, your heart listens to these ions, not with ears, but with the electrochemical sensitivity, shaped entirely by the dance of charged particles. Now shift upward to your brain. Here, rhythm becomes even more intricate. Your neurons fire in waves, some fast and sharp, others slow and dreamy. These brainwaves, delta, theta, alpha, beta, gamma, aren't abstract. They are the coordinated firing of millions of neurons, each guided by the flow of atomic signals. When you sleep, your brain doesn't turn off. It shifts its rhythm. Certain atoms flood in, others are drawn away. The levels of magnesium, calcium, and sodium influence how your neurons behave, how they rest, how they remember, how they dream. Even your temperature, your appetite, your sense of alertness, they all follow circadian rhythms. Roughly 24 hours, a cycle that persists even in darkness, anchored by molecular feedback loops. Proteins are built up during certain phases and broken down during others. Their presence activates or silences genes. The entire system resets each day, timed by atomic scale construction and decay. And the beauty is, this rhythm isn't unique to you. Plants track the sun, Animals migrate, flowers open and close, all of them driven by internal clocks that rely on the chemistry of atoms. Time isn't just something we measure, it's something we are. Your cells, without ever seeing a sunrise, still know when morning has come. The clock isn't on your wall, it's in your blood, your brain, your bones, in the atoms moving between protein and gene, between neuron and heart. Even the tiniest misalignment, a genetic mutation, a shift in environmental cues can disrupt this balance. That's why jet lag feels disorienting. Your atoms are still moving to the rhythm of another sky. But when it's working, when your body syncs with the world, there's a quiet sense of ease, a softness to waking, a steadiness to rest. And behind all of it, the same atoms we followed from stars to cells. They don't know they're keeping time, but they do. And in doing so, they give you rhythm, structure, peace. Tap your fingers on the surface beside you. It feels firm, definite, solid. Wood, glass, fabric, plastic. It doesn't matter. All of it seems real and tangible. A world you can touch, lean against, walk through without falling. Solidity is comforting, reliable, but it's also an illusion. Because the truth is, everything you can touch is almost entirely empty space. Let's start at the scale of the atom. You might remember that atoms are made of a central nucleus, composed of protons and neutrons, surrounded by a cloud of electrons. But what often gets lost in this picture is just how much space exists between those parts. If an atom were the size of a cathedral, the nucleus would be a dust mote hovering at the centre, and the electrons would be like whispering gnats near the walls. Everything else? Empty. So why doesn't your hand fall through your chair? Why can't you walk through a wall? Why doesn't the floor give way with each step? It's not because particles are bumping into each other, it's because of forces. Electrons, which surround every atom, carry negative charge. When you bring two objects close together, say, your hand and the surface of a table, the electrons in your skin repel the electrons in the table. The closer you get, the stronger the repulsion. You're not really touching the table, you're floating just above it, separated by an unimaginably tiny gap, held in place by the electromagnetic field. That firmness you feel, that's the resistance of those repelling charges, a force, not a collision. Touch is not contact, it's interaction. This isn't just a poetic thought, it's physics, and it's true for everything. A rock seems solid because the atoms within it are locked into a structure by shared forces, but zoom in far enough and you'll see the same thing. Empty space, charged fields, probability clouds. Solidity is a shared agreement between particles. We'll hold this shape for now. And the shape they hold is mostly scaffold, mostly potential. The firmness we trust is made not of substance, but of the tension between emptiness and resistance. Even the air around you, though invisible, is not nothing. It's full of atoms and molecules bouncing, jostling, occasionally colliding. And yet even those collisions happen without parts truly touching. They influence one another through invisible lines of interaction. It's strange, isn't it? To realise that the world you live in, stand on, breathe in, hug, carry, build, is not made of solidity, but of structure suspended in space, like a vast cathedral of silence lit by occasional sparks, and yet it works, it holds, it comforts. Because what matters isn't that atoms are mostly empty, it's that their arrangement creates the illusion of fullness, that from this dance of distance and charge, we get warmth, pressure, texture, and form. You are not solid in the way you might think, but you are stable, beautifully, gently stable, because the atoms in you, though separated by space, know how to hold hands across a distance, and from that invisible reach comes everything we call real. For all we know about atoms, their components, their charges, their interactions, there's still so much we don't. They're familiar yet strange, defined yet elusive. We can describe them with math, with models, with probabilities. But the moment we try to grasp them too tightly, they slip into uncertainty. An electron, for instance, has no precise location. Not really. Instead, it exists as a cloud of probability, a region where it might be, until we measure it. Then suddenly it appears. But in doing so, we lose information about its momentum. If we try to measure the momentum precisely, its location becomes a blur again. This isn't just a quirk of instruments. It's a fundamental truth of quantum mechanics. Known as the Heisenberg uncertainty principle, it tells us that some things in the atomic world are not just unknown, they are unknowable, at least simultaneously. It's a quiet limit, and it asks something rare of us: acceptance, not of confusion, but of mystery. We can calculate the energy levels of an atom with extraordinary accuracy. We can predict how it will bond, how it will behave in magnetic fields, how it will vibrate in a molecule. But when we try to ask, what is an electron really? Or why does the quantum world behave this way? The answers grow soft, poetic. We know so much, and yet, in the heart of what builds everything, there's a kind of silence. Maybe that's not a flaw. Maybe it's a gift. Because wonder doesn't need complete understanding. It simply needs presence. To sit with the atom is to sit with a mystery that is not threatening, but inviting. You are made of these little puzzles. They spin and flutter and hum inside you, shaping thoughts you'll never trace, feelings you'll never measure. And they don't ask to be solved, only noticed, only appreciated. The great physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." And he didn't mean that we're failing. He meant that even those who know the equations still find themselves face to face with something that transcends simplicity. We can use atoms, build with them, balance equations, predict outcomes. But the full why the universe is arranged this way, why matter behaves so precisely and yet so unpredictably, that remains a quiet space. A space for poets, for dreamers, for the curious, and for you. Maybe that's the most beautiful use of an atom. Not to measure it, not to split it, not to trap it in a diagram, but to simply wonder at it. To sit perhaps with your hand resting on your chest, feeling your breath, and realize everything you are is built from things you cannot fully explain, and that's okay. The mystery was never meant to be a wall, it was always meant to be a window. So here we are. We've drifted across billions of years and uncountable light years, through fiery beginnings, stellar births, quiet molecules, and the tiny dances of thought. And as we settle into stillness, let's look back, softly, gently, on the path we've followed. It began with nothing, and then, not nothing. A sudden bloom of everything: space, time, heat, and motion. In those first moments after the Big Bang, the universe was too hot, too chaotic, for anything as gentle as an atom to exist. It was only plasma, wild, searing, shapeless. Then came calm. Protons and neutrons formed. Then, after a long pause, electrons found homes in quiet orbits. The universe grew transparent. Atoms, simple hydrogen and helium, came into being, and with them the story of form began. But it wasn't enough to simply exist. Atoms wanted to gather, and so they did, under the pull of gravity, forming clouds, stars, galaxies. In the hearts of those early stars, atoms fused into heavier elements: carbon, oxygen, iron, the building blocks of life. And when those stars died, they scattered these gifts into space. Supernovae blew elements outward. Dust formed planets, and eventually Earth. Here, atoms formed water, air, minerals. They combined into molecules. They linked and folded and tangled into life. They became cells, and those cells became you, your breath, your bones, your thoughts. Every part of you is an arrangement of atoms that once belonged to something else: a mountain, a tree, a star. They've travelled through fire and silence to reach you. But they didn't stop there. These atoms move within you, even now. They carry oxygen through your bloodstream. They form proteins, repair cells, transmit signals. They help you heal. They help you dream. They remember the patterns of your heartbeat. They whisper the rhythm of waking and rest. And even though they are small, so small, they are the reason anything is anything. You're not made of separate pieces. You're made of relationships between atoms, bonds, spaces, forces holding shape. You're a choreography, a momentary pattern in a long, ongoing dance. We talked about what keeps those atoms together. Strong forces in the nucleus, delicate electron shells, the balance of repulsion and attraction. We explored how atoms build, bond, age, and eventually decay, and we watched as they returned, through death, through entropy, to the cosmos that birthed them. And now we've arrived here, not at an ending, but at a pause, a quiet breath at the edge of knowing. Because the most extraordinary part is this. Through it all, through galaxies and gravity and glowing stars, those same atoms now sit calmly inside you. Not to explode, not to flee, but to hold you together, to form the self that listens, feels and rests. That's where this journey always led, not to something beyond you, but to something within you. And as your thoughts begin to slow, as the quiet deepens, let that truth settle in. You are made of everything the universe has ever known, and the universe in turn is shaped by you, because for this moment, it is you. You've heard the phrase before, you're stardust. It sounds poetic, dreamlike. A bedtime phrase whispered to a child staring at a sky full of stars. But it isn't just metaphor, it's literal truth. The carbon in your bones, the oxygen in your lungs, the iron that pulses through every beat of your heart. None of it was born on Earth. None of it was part of the original universe, hot and new. These elements were made in stars. Stars, those distant fires in the dark, are not just light makers. They are element forges. Inside their cores, where temperatures climb into the millions and gravity crushes inward with unstoppable strength, hydrogen atoms fuse. They become helium. Then, with time and pressure, helium becomes carbon, carbon becomes oxygen, and on, all the way to iron. But the star cannot hold these heavier elements forever. Eventually it dies. Some quietly, some in an explosion so powerful it lights up entire galaxies for weeks. And in that explosion, the heavy elements are released, thrown into space, scattered across light years. That's where you come in. Because the Earth, your home, your soil, your trees, your oceans, formed from that scattered dust. And so did your body. Every atom of calcium in your teeth, every drop of nitrogen in your cells, every sulfur bond in the curl of your hair, made in stars. And just like those stars, you glow too, though more softly. The warmth of your body is the residue of countless molecular reactions, the tiny frictions of atoms moving, building, breaking, a constant quiet hum of being alive. When you lie still, feeling that warmth beneath a blanket or tucked into a pillow, you are holding a piece of cosmic history, not in your mind, but in your matter. And just as stars don't shine forever, neither will you. That isn't something to fear, it's something to honour. Because when the pattern of you comes to rest, your atoms won't vanish. They'll continue. They'll rest for a while. Then they'll rise again. Maybe in soil, maybe in song, maybe in the breeze that brushes the leaves of a tree you'll never see. Your story becomes someone else's beginning. That's the lullaby of stardust. Not that you burn forever, but that your light is shared, passed along, echoed. So tonight as you rest, know this. You're not small. You're not separate. You are woven from stars, from distant ancient light, and you carry their patience, their power, their peace. Let that truth settle gently in your chest. Let it loosen your breath. Let it soften your thoughts. And if sleep comes, let it find you as you are, a quiet constellation, a resting pattern of stardust, drifting gently back into the universe that made you. And now, we come to the quietest part of the journey, not because we've run out of things to say, but because this is where the story shifts from words to rest. You've heard the journey, how atoms formed in the first light of creation, how they weathered stars and silence, how they built the world and you. You've followed them through structure and breath, through aging and return, through patterns, mystery and stillness. And now, those same atoms that once drifted through starlight are here, in your breath, in the gentle weight of your chest as it rises and falls, in the calm of your muscles slowly softening as sleep draws near. They are not hurrying, neither should you. There is no need to remember everything, no need to grasp at each idea. The science has done its part. Now, let it dissolve, like sugar stirred into warm tea, into the soft hum of your body simply being. You are held by gravity, yes, by the bed beneath you, but also by structure, by trillions of tiny agreements between atoms to keep you whole for just a little longer. They don't know who you are, but they obey your shape, they echo your breath, they carry your warmth. Even in sleep they do not pause. Cells repair, neurons fire in gentle waves, molecules shift, quietly preparing you for morning. It's not effort, it's not noise, it's a rhythm, steady, simple and sure. And when you sleep, you join the rest of the universe in its quiet side. The Earth continues to turn, the moon hangs patiently. Somewhere distant galaxies keep their slow spin, but you don't need to follow them now. You've followed far enough. Now it's your turn to rest. Let your thoughts drift. They don't have to make sense. Let them blur at the edges like clouds melting into dusk. Feel the stillness beneath you. Let it rise. Let it carry you. And if your eyes close, let them. If your breath deepens, let it. Sleep is not the absence of you. It is your atoms in retreat, in recovery, in trust. They will hold you through the night as they've held you since the beginning. And when morning comes, if it comes, you'll still be there. The atoms will still be listening, still arranging themselves just so to bring you into wakefulness again. But for now, let go. Let gravity have you. Let time pass without notice. Let sleep carry the pattern of you, safely, gently, into its dark and quiet places. Because nothing is more natural, more ancient, more cosmic than the need to rest. Good night, Stardust. Sleep well.